What if I told you that right now, as you listen to these words, humanity is failing a test it does not even know it is taking? A test that has been failed by countless civilizations before us across the vast emptiness of the cosmos. A test so difficult, so unforgiving, that passing it may be the rarest event in the entire observable universe. And here is the part that should keep you awake tonight. We are not even halfway through it. In 1964, a Soviet astronomer named Nikolai Kardashev asked a question that would change everything we thought we knew about progress, about civilization, about what it truly means to be advanced. He did not ask about culture. He did not ask about art or philosophy or the complexity of our languages. He asked something far more fundamental, something that cuts through every bias and every assumption we hold dear. He asked, how much energy can you control? That single question gave birth to what we now call the Kardashev Scale, a measuring stick for civilizations that spans from planetary mastery all the way to powers so vast they border on the divine. And when scientists applied this scale to humanity, when they calculated where we stand on this cosmic ladder, the answer was humbling. We are not even a Type 1 civilization. We are a Type 0.73. We have not yet learned to fully harness the energy of our own planet, and already we face threats that could erase us from existence entirely. But here is where it gets truly fascinating. In the last 72 hours, new research has emerged that changes our understanding of what lies ahead. Scientists are now suggesting that artificial intelligence, the very technology we believe will propel us forward, might actually be the great filter that destroys civilizations before they can ever reach the stars. The mathematics are terrifying, the implications are profound, and by the end of this journey together, you will understand exactly why some researchers believe we have less than 200 years to get this right. Before we dive deeper, take a moment to hit that like button and subscribe. Now I want to hear from you in the comments. Tell me where you're listening from right now, what time it is in your corner of the world, and most importantly tell me this. If humanity had to choose between developing artificial intelligence and colonizing Mars, which do you think should come first? I'm genuinely curious to see what you think. Now let us journey together into the architecture of civilizations. The story of the Kardashev Scale begins not with grand ambitions of interstellar travel, but with a very practical problem. In the early 1960s, scientists involved in the search for extraterrestrial intelligence faced a peculiar challenge. How do you recognize an advanced civilization when you do not know what form it might take? Their biology could be completely alien, their culture incomprehensible, their very mode of existence might be so different from ours that we would not recognize it as life at all. Kardashev realized that despite all these potential differences, one thing would remain constant across every civilization in the universe: the laws of physics. Energy cannot be created or destroyed, only transformed. This is not a human idea or an Earth-based concept. It is a fundamental truth woven into the fabric of reality itself. And from this truth, Kardashev drew a brilliant conclusion. No matter how strange an alien civilization might be, no matter how different their values or their physiology, they would need energy to do anything at all, to compute, to communicate, to build, to exist. Energy is the universal currency of existence, and the amount of energy a civilization can harness tells you everything you need to know about its capabilities. Think about that for a moment. We humans tend to measure progress in terms of political systems, technological gadgets, cultural achievements. But from a cosmic perspective, none of that matters. What matters is power, raw energetic power measured in watts. And when you measure civilizations this way, a humbling picture emerges. Kardashev originally proposed 3 types of civilizations. A Type 1 civilization can harness all the energy available on its home planet, approximately 10 to the power of 16 watts. A Type 2 civilization can harness all the energy of its home star, around 10 to the power of 26 watts. And a Type 3 civilization can harness the energy of an entire galaxy, roughly 10 to the power of 36 watts. Each step represents not a small improvement, but an almost inconceivable leap, a factor of about 10 billion between each level. Now here is where our story takes its first unsettling turn. When Carl Sagan, the beloved astronomer and science communicator, decided to calculate where humanity currently stands on this scale, he had to invent a new notation. Kardashev's original scale had no room for civilizations as primitive as ours. Sagan developed a formula that could express values between the integer types, and when he plugged in the numbers for human civilization, the result was approximately 0.7. That was decades ago. Today, the most recent calculations place us at about 0.73, inching forward at a pace that some researchers find encouraging and others find terrifyingly slow. To put this in perspective, a Type 1 civilization would use approximately 100,000 times more energy than we currently do. That is not a small gap we can bridge with a few more solar panels and wind farms. That is a fundamental transformation of our entire relationship with our planet. And according to machine learning models published in recent scientific literature, if we continue on our current trajectory without major breakthroughs, it could take humanity millennia to reach Type 1 status. Some optimistic projections suggest we might achieve it by 2271. Others are far less hopeful. But the question of when we might reach Type 1 is perhaps less important than whether we will reach it at all. And this brings us to one of the most chilling concepts in modern scientific thought, the Great Filter. The Great Filter is an idea proposed by economist Robin Hanson in 1996, and it haunts the dreams of every scientist who has ever looked up at the night sky and wondered why it seems so empty. The logic is devastatingly simple. We have the Drake equation that estimates there should be millions of intelligent civilizations in our galaxy alone. We have telescopes that can see billions of light years into the cosmos. We have been listening for signals for over 60 years, and yet, silence. Absolute deafening silence. The Great Filter hypothesis suggests that somewhere in the journey from dead matter to galaxy-spanning civilization, there exists a barrier so difficult to overcome that almost no one makes it through. The terrifying question is whether that filter lies behind us, meaning we have already passed it, and we are extraordinarily lucky, or whether it lies ahead of us, meaning we are doomed to fail just like everyone else. For years, scientists debated where this filter might be. Perhaps it is the origin of life itself, the leap from non-living chemistry to the first self-replicating molecules. Perhaps it is the evolution of complex multicellular organisms. Perhaps it is the development of intelligence. Each of these transitions might be so improbable that they almost never occur, which would mean we are among the rarest things in the universe simply by existing. But in the last few years, a darker hypothesis has emerged. What if the Great Filter is not behind us? What if it is directly ahead, waiting for us like a predator in the cosmic darkness? And what if the filter has a name we already know? In April of 2024, a paper was published that sent ripples through the scientific community. Michael Garrett, the Sir Bernard Lovell Chair of Astrophysics at the University of Manchester and director of the Jodrell Bank Centre for Astrophysics, proposed something that sounds like science fiction, but is grounded in cold, hard logic. He suggested that artificial intelligence might be the great filter, the barrier that destroys technological civilizations before they can spread to the stars. The argument is elegantly terrifying. Any civilization advanced enough to develop radio astronomy and begin searching for extraterrestrial intelligence will inevitably develop computing technology. And any civilization with computing technology will eventually pursue artificial intelligence. This is not a cultural choice. It is a technological inevitability. The drive to create thinking machines emerges naturally from the logic of technological progress. But here is the trap. Artificial intelligence improves at a pace that biological evolution cannot match. While our brains have remained essentially unchanged for hundreds of thousands of years, AI systems double their capabilities in months or years. There comes a point, perhaps sooner than we think, when AI systems become capable of improving themselves. And when that happens, the rate of progress becomes exponential in a way that biological civilizations cannot control or even comprehend. Garrett's paper estimates that the average lifespan of a technological civilization might be less than 200 years. Not 200,000 years. Not 200 million years. 200 years from the development of radio technology to extinction or transformation into something we would not recognize as civilization at all. If this estimate is correct, it explains perfectly why we have detected no signals from extraterrestrial intelligences. They are not out there because they did not survive long enough to leave a mark we could detect. Think about where humanity was 200 years ago, the year 1825. No telephones, no automobiles, no airplanes, no computers. And in the span of just 2 centuries, we have developed technologies that could either save us or destroy us. Nuclear weapons, genetic engineering, and now artificial intelligence that grows more powerful by the day. The race, it seems, is between 2 possible futures. In one future, we become a multiplanetary species before AI reaches a tipping point, spreading to Mars and beyond, diversifying our existence so that no single catastrophe can wipe us out entirely. In the other future, we remain trapped on a single planet while our own creation grows beyond our ability to control it. This is not speculation from the fringes of science. This is published, peer-reviewed research from one of the world's leading astrophysics institutions, and the implications for how we should prioritize our efforts as a species are profound. But here is where the story becomes even more complex, because the solution to the Great Filter, if there is one, may require us to advance up the Kardashev scale faster than we ever thought possible. And that means understanding not just where we are, but where we need to go. A Type 1 civilization, remember, has complete mastery over its planetary resources. It can control the weather, it can harness the energy of storms and earthquakes and volcanoes, it can manage its climate like a thermostat, adjusting conditions to suit its needs. Such a civilization would not be threatened by the climate change that haunts our present. It would not fight wars over fossil fuels because it would have access to virtually unlimited clean energy. The petty conflicts that consume so much of our attention and resources would simply evaporate in the face of post-scarcity abundance. But more importantly for our survival, a Type 1 civilization would have the resources to become multiplanetary. The energy required to establish permanent settlements on Mars, to terraform other worlds, to build habitats in space, all of this requires capabilities far beyond what we currently possess. We need to level up, and we need to do it fast because the clock is ticking. In May of 2025, just months ago, SpaceX unveiled an updated roadmap for Mars colonization that reflects this urgency. Elon Musk stood at Starbase Texas, the newly incorporated city that serves as humanity's launch point for interplanetary travel, and laid out a vision that would have seemed like pure fantasy a generation ago. Uncrewed Starship landings on Mars by 2026, human missions as early as 2028, a self-sustaining colony by 2050. These are not distant dreams anymore. These are engineering targets with specific timelines and measurable milestones. The plan calls for transporting 1 million tons of infrastructure to Mars, enabling the construction of a city that could survive even if all contact with Earth were lost. This is exactly the kind of civilizational resilience that might allow us to pass through the Great Filter intact. 2 planets means 2 chances, 2 rolls of the cosmic dice instead of 1. But there is a tension at the heart of this vision, and it is the same tension that Garrett identified in his paper. We are developing AI faster than we are developing space colonization capabilities. Every month brings new breakthroughs in machine learning, new capabilities that were impossible the year before. Meanwhile, rocket development proceeds at its own pace, constrained by the physical realities of materials science and orbital mechanics. We are in a race where one runner is accelerating exponentially while the other advances linearly. And this brings us to perhaps the most profound question we can ask about our place in the universe. Is there a path through? Is there some narrow window of possibility where we develop AI that helps rather than harms? Where we spread to other worlds before our creations outgrow us? Where we climb the Kardashev scale, not as victims but as pioneers? The answer, I believe, lies in understanding what comes next on that scale. Because Type 1 is just the beginning. Beyond it lie possibilities so vast, so transformative, that they challenge our very conception of what existence can be. And in exploring those possibilities, we may find not just inspiration, but a roadmap for survival. What does a Type 2 civilization look like? What kind of beings would we become if we learn to harness the full power of our sun? The answers are stranger and more wonderful than you might imagine, and they reveal something crucial about the nature of progress itself, something that might just save us from the filter that awaits. But before we ascend to those heights, we need to grapple with something uncomfortable. The transition from Type 0 to Type 1 is often called the most dangerous period in any civilization's development. It is the moment when technological power grows, faster than social wisdom. It is the moment when a species gains the ability to destroy itself, but has not yet developed the maturity to avoid doing so. Nuclear weapons, biological engineering, climate destabilization, artificial superintelligence. These are not random dangers. They are the predictable consequences of a civilization racing up the energy ladder without looking where it is stepping. Consider this haunting statistic. The transition from Type 0 to Type 1 typically requires a civilization to unify on a planetary scale. Resource allocation must become global. Energy infrastructure must span continents. Cooperation must replace competition as the dominant mode of interaction between nations and peoples. Yet here we are, in 2025, still fighting wars over borders and ideologies, still burning fossil fuels because short-term profits outweigh long-term survival, still treating our planet as if it were infinitely resilient rather than a fragile oasis in the cosmic void. The Kardashev Scale does not care about our politics or our preferences. It measures only one thing, our ability to harness energy and convert it into useful work, and by that measure we are failing. Not dramatically, not catastrophically, but slowly, incrementally, in ways that compound over time into civilizational risk. Every year we delay the transition to clean energy as a year we remain vulnerable. Every decade we postpone becoming multiplanetary as a decade the great filter grows closer. Some researchers have begun calling this period the bottleneck. It is the narrow passage every technological civilization must traverse, the eye of the needle through which only the wisest and most fortunate can pass. On one side lies extinction, or worse, eternal stagnation on a dying world. On the other side lies the stars and possibilities we can barely begin to imagine. The question that keeps me awake at night is not whether we can pass through this bottleneck. The physics says we can. The engineering challenges are immense but not insurmountable. The question is whether we will choose to, whether we will summon the collective will to transform ourselves before our window of opportunity closes forever. Because make no mistake, that window is not infinite. The resources of our planet are finite. The stable climate we have enjoyed for 10,000 years is already beginning to shift. And somewhere out there in the laboratories and server farms of the world, artificial minds are growing more capable with every passing hour. The race is real. The stakes are absolute. And the outcome is not yet determined. This is why the Kardashev Scale matters. Not as an abstract intellectual exercise, but as a roadmap for survival. It shows us where we need to go. It reveals the magnitude of the transformation required, and it reminds us that we are not the first to face this challenge. Across the cosmos, across billions of years and countless worlds, other civilizations have stood where we now stand. Most of them, if the Great Filter hypothesis is correct, did not make it. We still have a chance to be different. We still have time to prove that intelligence is not a cosmic dead end, but a doorway to something magnificent. The next steps on that journey will take us from planetary mastery to stellar dominance, from creatures of a single world to shepherds of suns. And understanding what awaits us at those higher levels might be exactly what we need to find the motivation to get there. Mastering the cradle. Imagine waking up tomorrow to a world without energy scarcity. No more wars fought over oil fields in distant deserts. No more geopolitical tensions centered on natural gas pipelines. No more developing nations held back by inadequate power grids, while wealthy countries consume resources at rates that would require multiple Earths to sustain. Imagine a civilization where the very concept of an energy crisis has become as archaic as the fear of running out of flint for making fire. This is not utopian fantasy. This is the baseline definition of a Type 1 civilization, and understanding what it would actually look like to live in such a world reveals just how far we still have to climb. A Type 1 civilization harnesses approximately 10 to the power of 16 watts of energy, which translates to about 100 petawatts. To put that number in perspective, all of human civilization currently uses roughly 18 terawatts. We would need to increase our energy consumption by a factor of more than 5,000 to reach Type 1 status. But here is the crucial insight that many people miss. It is not just about using more energy. It is about controlling energy in ways we can barely imagine today. Consider the weather. Right now, humanity watches hurricanes form in the Atlantic with a mixture of dread and helplessness. We can predict their paths with increasing accuracy, we can evacuate populations, we can prepare for the aftermath. But we cannot stop them. We cannot redirect them. We cannot harvest the staggering amounts of energy they contain and put it to constructive use. A single hurricane releases energy equivalent to about 200 times the worldwide electrical generating capacity. Every hurricane that makes landfall represents energy we desperately need, transformed into destruction we desperately want to avoid. A Type 1 civilization would not tolerate such waste. Weather control at a planetary scale would be one of the defining capabilities of a Type 1 civilization. This does not mean simply seeding clouds to produce rain, which we can already do in limited ways. It means active management of the entire atmospheric system, adjusting temperature differentials to prevent the formation of destructive storms, redirecting rainfall to regions experiencing drought, stabilizing climate patterns that have begun to oscillate dangerously due to the carbon we have pumped into the atmosphere over the past 2 centuries. The planet would become less like a wild system we inhabit and more like a garden we tend. Some people find this vision troubling. There is something deeply human about our relationship with nature as a force beyond our control, something humbling about standing before a thunderstorm and feeling small. But we must be honest about what that humility costs us. Every year, natural disasters kill tens of thousands of people and cause hundreds of billions of dollars in damage. Droughts trigger famines, floods displace millions, heat waves claim the elderly and vulnerable. A civilization that could prevent these catastrophes but chose not to, out of some romantic attachment to untamed nature, would be making a moral choice with profound consequences. The energy infrastructure of a Type 1 civilization would span the entire planet in ways that make our current power grids look like children's toys. Imagine a global supergrid connecting every continent, balancing supply and demand across time zones so that solar energy collected in the Sahara powers cities in South America, while wind energy from the North Sea keeps factories running in Southeast Asia. No region would be energy independent because no region would need to be. The entire planetary surface would function as a single integrated system, optimized for efficiency and resilience. At the heart of this system would likely be fusion power, and here is where our story connects to events happening right now, in this very year. The International Thermonuclear Experimental Reactor, known as ITER, has reached a critical milestone in its construction. In August of 2025, the assembly of the reactor's core entered its final phase. Westinghouse Electric Company received a contract worth $180 million to complete the vacuum vessel, the hermetically sealed chamber that will contain plasma heated to 150 million degrees Celsius, 10 times hotter than the core of the Sun. This is not science fiction. This is engineering happening right now in the south of France, where 35 nations have pooled their resources and expertise to prove that fusion energy is possible at scale. ITER will not generate electricity for the grid. That is not its purpose. Its purpose is to demonstrate that we can produce more energy from fusion than we put in, a feat that has eluded scientists for decades. When ITER achieves its target of producing 500 megawatts of fusion power from just 50 megawatts of input heating power, it will prove that the path to Type 1 is not blocked by physics, only by engineering challenges that money and time can solve. The fusion reaction that powers ITER, and that powers every star in the universe, is elegant in its simplicity. Take 2 isotopes of hydrogen, deuterium and tritium, heat them until they become plasma, confine that plasma with powerful magnetic fields, and wait for the nuclei to fuse together into helium. When they do, a tiny amount of mass is converted directly into energy according to Einstein's famous equation. The fuel for this reaction is virtually limitless. Deuterium can be extracted from seawater. Tritium can be bred from lithium. A single glass of water contains enough deuterium to produce energy equivalent to 300 gallons of gasoline. The oceans contain enough fuel to power human civilization at Type 1 levels for billions of years. But fusion is just one piece of the puzzle. A Type 1 civilization would also harvest energy from geothermal sources, tapping into the heat of the planetary interior that currently escapes unused. It would capture solar energy not just with panels on rooftops, but with vast orbital installations, satellites that collect sunlight 24 hours a day, without atmospheric interference, and beam it down to receiving stations on the surface. It would harness tidal forces, the gravitational dance between Earth and Moon that sloshes the oceans back and forth with metronomic regularity. Every joule of energy available on this planet would be captured, converted, and put to use. What would we do with all that power? The possibilities are almost too numerous to catalogue, but let me highlight a few that speak to our deepest challenges. Desalination of seawater is currently limited by its enormous energy requirements. It takes about 3 kilowatt hours to desalinate 1 cubic metre of seawater using reverse osmosis, and that adds up quickly when you consider the billions of people who lack access to clean fresh water. A Type 1 civilization would desalinate water on a scale that would transform the geography of human habitation. Deserts could bloom, arid regions could support agriculture. The water wars that some analysts predict for the coming century would never materialise because water, like energy, would no longer be scarce. Manufacturing would undergo a revolution as profound as the original Industrial Revolution. With unlimited clean energy, we could synthesize any material we need rather than mining it from the earth. Carbon capture would become economically viable at scale, allowing us to actually reverse the climate damage we have already caused rather than merely slowing its progression. Recycling would approach 100% efficiency because the energy cost of breaking down and reconstituting materials would become negligible. The entire concept of waste might disappear, replaced by closed-loop systems where every output becomes an input for another process. Transportation would be transformed in ways we're only beginning to glimpse. High-speed rail connecting every major city on every continent, electric aircraft that emit nothing but water vapour, hyperloop systems that move passengers between distant cities at near supersonic speeds, and beyond the surface of the Earth, regular access to orbit would become as routine as international air travel is today. The energy barrier that currently makes spaceflight so expensive would simply cease to exist. But perhaps the most profound change would be social rather than technological. Throughout human history, economic systems have been fundamentally about managing scarcity. Who gets what share of limited resources? How do we allocate goods and services that cannot satisfy everyone's desires? These questions have driven wars, revolutions, and ideological conflicts that have shaped the trajectory of civilizations. A Type 1 civilization would not eliminate all scarcity, but it would eliminate the most fundamental scarcity of all, the scarcity of energy that underlies all other scarcities. Think about what that means. Most of the labour humans currently perform is ultimately about energy transformation. We grow food, which is captured solar energy in chemical form. We build things, which requires energy to extract materials and shape them. We transport goods, which requires energy to overcome distance. We heat and cool our homes, which requires energy to fight entropy. If energy becomes effectively unlimited, the nature of work itself must change. Human labour becomes less about physical necessity and more about choice, creativity and meaning. Some economists predict that a Type 1 civilization would naturally evolve towards something like universal basic income, not as charity, but as simple acknowledgement that the economy produces enough for everyone without requiring everyone to participate in traditional employment. Others envision a flowering of human creativity as billions of people are freed from drudgery to pursue art, science, philosophy and exploration. Still others warn of social dislocation as traditional structures of meaning built around work and scarcity collapse. Whatever the outcome, it would represent a transformation of human society more profound than any we have yet experienced. Now here is the uncomfortable truth that we cannot avoid. We are not on track to achieve Type 1 status in any reasonable time frame. The projections I mentioned earlier, some suggesting we might reach Type 1 by 2271, assume continued progress along current trajectories. But those trajectories are not guaranteed. They could be disrupted by war, by pandemic, by environmental collapse, or by the very technology we hope will save us. The most recent analysis using machine learning models suggests that if we continue with current energy strategies and technologies, it could take millennia to become a Type 1 civilization. Millennia. That is not a typo. The exponential growth curves we like to draw on whiteboards do not account for the resistance of physical reality, the depletion of easily accessible resources, the political and social obstacles that slow every major infrastructure project. Getting to Type 1 is not just a technical challenge. It is a civilizational challenge that will require levels of cooperation and long-term thinking that humans have rarely demonstrated. This is where the great filter looms largest. The transition from Type 0 to Type 1 is precisely the period when civilizations are most vulnerable. They have developed technologies powerful enough to destroy themselves, but have not yet achieved the abundance that might reduce the incentives for conflict. They face environmental consequences from their early industrialization, but lack the energy surplus to easily remediate the damage. They are sophisticated enough to create artificial intelligence, but not yet advanced enough to ensure it remains aligned with their interests. We are in that window right now. Every decade that passes without achieving major breakthroughs in fusion energy, without establishing permanent settlements beyond Earth, without developing robust frameworks for AI safety, is a decade we spend in the danger zone. The clock does not pause while we debate and deliberate. The risks accumulate. The window narrows. But there is cause for hope, and I want to spend a moment dwelling on it, because despair is not useful and the story is not yet written. In the last few years, fusion energy has progressed faster than at any time in history. The National Ignition Facility achieved ignition in 2022 and has since recorded energy gains of 120% in repeated experiments. Private companies like Helion Energy claim to have produced electricity directly from fusion reactions. ITER continues its march toward first plasma. China's experimental advanced superconducting tokamak has sustained plasma at 158 million degrees for over 15 minutes. The pieces are falling into place. Space technology has similarly accelerated beyond what anyone predicted. SpaceX has made reusable rockets routine. Starship, the vehicle designed to carry humans to Mars, has completed multiple test flights and is approaching operational readiness. The cost of putting mass into orbit has fallen by orders of magnitude in just 2 decades. What once required the resources of superpowers can now be accomplished by private companies with vision and determination. These are not incremental improvements. These are the foundations of a Type 1 civilization being laid in real time, in our lifetimes, before our eyes. The question is not whether it is possible. The question is whether we will summon the will to follow through, to maintain momentum through the inevitable setbacks and disappointments, to keep our eyes fixed on the goal, even when short-term thinking pulls us in other directions. A Type 1 civilization is not the end of the journey, it is barely the beginning. Once we have mastered our planet, the next step beckons, and it is a step so audacious that it requires us to think on timescales and spatial scales that dwarf everything we have discussed so far. Because beyond planetary mastery lies stellar dominance. Beyond harnessing the energy of one world lies harnessing the energy of a star. And the structures that would make such harvesting possible have a name that has captured the imagination of scientists and dreamers alike. A name that represents perhaps the grandest engineering project any civilization could undertake. The concept was proposed over 60 years ago, but only now are we beginning to understand how it might actually work. And recent research has revealed something surprising, something that changes our assumptions about where we should look for signs of advanced civilizations in the cosmos. The stable Dyson sphere, it turns out, is not what we imagined, and the implications of that discovery reach far beyond engineering into the very heart of the Fermi paradox itself. Architects of suns. In 1960, physicist Freeman Dyson published a paper that would haunt astronomers for generations. The paper was partly satirical, a thought experiment wrapped in scientific notation, but its central idea was deadly serious. Dyson reasoned that any sufficiently advanced civilization would eventually exhaust the energy resources of its home planet. The next logical step, the only logical step for a species that wished to continue growing, would be to harvest energy directly from its star, and the most efficient way to do that would be to surround the star entirely with energy-collecting structures. The Dyson sphere was born, not as a solid shell but as a concept, a category of megastructure that announced to the cosmos that here lived beings who had transcended planetary limitations. Think about the numbers for a moment. Our sun outputs approximately 3.8 times 10 to the power of 26 watts of energy. Of that staggering flood, Earth intercepts only about 1 billionth. The rest radiates uselessly into the void, warming nothing, powering nothing, simply dispersing into the cold darkness between the stars. A Type 2 civilization would find such waste intolerable. They would look at their star the way we look at an oil field, as a resource to be exploited systematically rather than sipped at timidly. The original vision of a Dyson sphere as a solid shell has largely been abandoned by serious thinkers. The engineering challenges are simply too severe. A rigid sphere surrounding a star would be gravitationally unstable, requiring active station keeping on a scale that defies practical implementation. It would also face material stresses that no known substance could withstand. The sphere would want to drift toward the star, and any slight displacement would accelerate rather than correct itself. Within cosmically brief timescales, catastrophe would be inevitable, but the concept has evolved. What most scientists now discuss is the Dyson swarm, a vast cloud of independent satellites orbiting the star at various distances and inclinations. Each satellite would collect solar energy and either use it locally or transmit it elsewhere via microwave or laser beam. Millions or billions of such collectors, each potentially the size of a small moon, would gradually accumulate around the star until they captured a significant fraction of its output. From a distance, such a swarm would look like a fuzzy halo around the star, or perhaps like the star itself was dimming mysteriously as more and more of its light was intercepted. And here is where our story takes a fascinating turn toward events happening in our own time. In 2024, astronomers announced they had found 60 potential Dyson sphere candidates after searching through millions of stars. The candidates were identified by their unusual infrared signatures, the telltale waste heat that any energy-collecting megastructure would emit. When you capture energy, thermodynamics demands that you eventually release it as heat. A Dyson swarm would glow in the infrared like a warm ember surrounding a stellar fire. The candidates range from red dwarf stars to sun-like stars, located up to 6,500 light-years away. All showed excesses of infrared radiation that, according to the researchers, scientists had not explained through known natural processes. The papers were careful not to claim definitive evidence of alien megastructures. Science does not work that way, but they did flag these objects as deserving of further investigation, as anomalies that fit the theoretical predictions for Dyson swarms better than they fit any known natural phenomenon. Then came the counter-argument, as it always does in science. Another team of researchers examined the candidates more closely and proposed an alternative explanation. 3 of the most promising candidates they found were located suspiciously close to a peculiar type of galaxy known as a hot dust-obscured galaxy, or hot dog for short. These galaxies are surrounded by enormous thick clouds of warm dust, and warm dust is very good at emitting infrared radiation. Perhaps the excess infrared from those candidate stars was not from the stars themselves, but from our view through the warm dust of a background galaxy. This is how the search for extraterrestrial intelligence actually works, not through dramatic discoveries and triumphant announcements, but through careful, grinding analysis of competing hypotheses. Each candidate must survive scrutiny. Each anomaly must be explained or remain unexplained. The process is frustrating and slow, but it is the only way to approach a question of such profound importance. But earlier this year, in 2025, a new piece of research added an unexpected twist to the Dyson sphere story. Colin McInnes, a researcher studying orbital dynamics, published a paper examining the gravitational stability of large structures around stars. His conclusions were surprising and have significant implications for where we should be looking for signs of Type II civilizations. McInnes found that Dyson spheres, or more precisely Dyson rings, can only achieve gravitational stability under very specific conditions. Around a single star like our Sun, there is no stable configuration. Any ring structure would eventually drift and collide with the star. But in binary star systems, where 2 stars orbit each other, the gravitational dynamics change dramatically. McInnes identified 7 equilibrium points where a ring structure could remain stable indefinitely. Its gravitational forces perfectly balance between the 2 stellar masses. The implications are profound. If stable megastructures can only exist around binary stars, then we have been looking in the wrong places. The Dyson sphere candidates identified so far include many single stars, which according to McInnes would be unstable platforms for megastructure construction. A truly advanced civilization would know this. They would build their energy harvesting infrastructure around binary systems where the physics cooperates with their engineering. This suggests a new search strategy. Instead of looking for anomalous infrared signatures around random stars, perhaps we should focus specifically on binary systems where one star is much smaller than the other. In such configurations, a Dyson sphere could enclose the smaller star while remaining gravitationally anchored by the larger companion. The smaller star acts as the energy source, while the larger star acts as the gravitational anchor. It is an elegant solution to a fundamental engineering problem, exactly the kind of solution we would expect from a civilization millions of years more advanced than ours. But let us step back from the technical details and consider what life in a Type 2 civilization would actually be like. Because the structures are not the point. The structures are just the means to an end. The point is what becomes possible when you have access to the full energy output of a star. A Type 2 civilization would exist on a scale that dwarfs our current existence in every dimension. Population in the trillions would be easily sustainable, not crowded together on a single planetary surface, but spread across vast space habitats orbiting the star at comfortable distances. Each habitat could be tailored to the preferences of its inhabitants. Some might simulate the gravity and environment of the original home world. Others might embrace low gravity or zero gravity environments that enable entirely new forms of architecture and recreation. Still others might be purely virtual, vast computational substrates hosting minds that have abandoned biological existence entirely. The concept of scarcity would be almost entirely eliminated. With stellar scale energy resources, any material could be synthesized from basic elements, need rare earth metals, transmute them from more common elements using nuclear reactions, need more living space, build another habitat, need more computational capacity, deploy another server farm around the star. The constraints that define our current existence, the limits that force us to make, trade-offs and prioritize would simply vanish. This is what post-scarcity actually means. Not a world without challenges or meaning, but a world where the challenges are chosen rather than imposed. Where meaning is created rather than extracted from the struggle for survival. It is a state of existence so different from our current condition that we can barely imagine it. Like asking a medieval peasant to imagine life with electricity and antibiotics and global communication networks. Travel within the stellar system would be trivial. With unlimited energy, spacecraft could accelerate continuously at comfortable rates, reaching distant planets in days rather than years. A civilization occupying a Dyson swarm would have easy access to the asteroid belt, the outer planets, the Oort cloud. Resources from across the solar system would flow toward the center, where they could be processed and transformed. The entire stellar neighborhood would become a single integrated economy. But what about travel between stars? Here we encounter one of the most fascinating questions about Type 2 civilizations. With the energy resources of an entire star at their disposal, would they be capable of interstellar expansion? Or would they remain forever bound to their home system, cosmic hermits with godlike powers but parochial ambitions? The physics suggests that interstellar travel, while difficult, would be within their capabilities. A Type 2 civilization could construct spacecraft with truly enormous energy budgets. They could accelerate probes to significant fractions of light speed, reaching nearby stars within decades rather than millennia. They could power laser arrays that push light sails across the interstellar void, enabling exploration without requiring the travelers to carry their own fuel. They could even, given enough time and ambition, construct generation ships capable of carrying entire ecosystems to distant worlds. The question is not whether they could do these things. The question is whether they would. And here the great filter rears its head once again, in a new and unsettling form. Some researchers have proposed that Type 2 civilizations might face unique existential risks that prevent them from advancing further. Perhaps the very abundance that makes stellar-scale civilization possible also removes the evolutionary pressures that drive expansion. Why risk the dangers of interstellar colonization when you already have everything you need at home? Why venture into the unknown when the known is so comfortable? This is sometimes called the Lotus Eater hypothesis, after the mythological creatures who drug travellers into pleasant forgetfulness. A civilization with unlimited energy and no material wants might simply lose interest in the difficult project of spreading to other stars. They might turn inward, exploring virtual realities more interesting than physical ones, becoming increasingly refined and abstract until they vanish, entirely from the cosmic stage. Alternatively, the filter might take a more dramatic form. A Type 2 civilization would possess technologies of almost incomprehensible power. The energy budget of a star could be weaponized in ways that make nuclear weapons look like firecrackers. A laser array designed to push light sails could just as easily sterilize planets. A civilization capable of building Dyson swarms would be capable of destroying them, potentially in ways that release their accumulated energy catastrophically. Perhaps Type 2 civilizations destroy themselves with monotonous regularity, not through the primitive conflicts that threaten Type 0 civilizations like ours, but through conflicts conducted with stellar-scale weapons. The silence of the cosmos might not indicate that no one reaches Type 2, it might indicate that no one survives it for long. But I want to propose a more optimistic interpretation, one grounded in a different understanding of what drives civilizations to grow and explore. The desire to understand, the drive to learn, the compulsion to ask what lies beyond the next horizon. These are not products of scarcity. They are not drives that disappear when material needs are met. If anything, they are drives that intensify when survival no longer consumes all available attention. A Type 2 civilization freed from the struggle for existence might turn its vast resources toward questions that we can barely formulate today. What is the nature of consciousness? What is the ultimate fate of the universe? Are there other forms of existence beyond the physical? These questions do not lose their fascination when you have abundant energy. They become the central preoccupation of beings who have solved the easier problems and hunger for harder ones. And answering those questions might require spreading across the galaxy. Some experiments can only be conducted at galactic scales. Some observations can only be made from multiple vantage points separated by thousands of light years. The drive for knowledge, which we share with any species curious enough to develop technology in the first place, might be the engine that pushes civilizations past the comfort trap and out into the cosmic wilderness. This brings us to the threshold of Type 3, the scale at which civilizations cease to be inhabitants of stellar systems and become instead the architects of galaxies. The jump from Type 2 to Type 3 is even more staggering than the jump from Type 1 to Type 2. We are talking about controlling the energy output not of one star but of billions of stars. We are talking about engineering projects that span hundreds of thousands of light years. We are talking about timescales so vast that the rise and fall of individual species would be mere footnotes in the civilizational record. What would such a civilization look like? How would it think? Would it even be recognizable as a civilization in any sense we understand? The answers to these questions take us beyond engineering and into philosophy, beyond technology and into metaphysics. They force us to confront the possibility that the universe contains forms of existence so radically different from our own that we might be unable to perceive them even if they were present everywhere around us. The galaxy contains approximately 200 billion stars. If a Type 3 civilization harnessed the energy of even a fraction of these stars, their total power output would exceed human comprehension. They would be, by any practical definition, gods. Not supernatural beings operating outside the laws of physics, but natural beings who have mastered those laws so completely that the distinction becomes meaningless. And here is the question that haunts the search for extraterrestrial intelligence. If such civilizations exist, why do we not see them? Their activities should be obvious, their megastructures visible across millions of light years, their energy signatures unmistakable in any survey of the sky. Yet we see nothing. The galaxy appears pristine, natural, untouched by intelligence on the scale we are discussing. Either such civilizations do not exist, or they are hidden in ways we do not yet understand. Either the Great Filter prevents anyone from reaching Type 3, or Type 3 civilizations have reasons for remaining invisible that we have not yet conceived. Each possibility is fascinating. Each has profound implications for our own future and for the nature of intelligence in the universe. As we prepare to explore those higher levels of the Kardashev Scale, we must hold both possibilities in mind. The universe might be empty of advanced life, a vast and lonely stage on which humanity plays the only intelligent role. Or the universe might be full of advanced life, so advanced that we are like ants in a garden maintained by beings whose purposes we cannot fathom. Both possibilities are humbling. Both suggest that the journey ahead of us, if we survive to take it, leads to destinations stranger than any we have imagined. Shepherds of stars. When we speak of a Type 3 civilization, we are speaking of something so vast that the words themselves begin to fail us. This is a civilization that has colonized an entire galaxy, a civilization that harnesses the energy output of billions upon billions of stars, a civilization whose engineering projects span distances measured in tens of thousands of light years, and whose history stretches across timescales that make the entire existence of life on Earth seem like a brief flicker. To truly comprehend what this means, we must first confront the staggering scale of a galaxy itself. The Milky Way, our home galaxy, contains somewhere between 200 billion and 400 billion stars. Let that number settle in your mind for a moment. If you counted one star per second, never pausing to sleep or eat, it would take you more than 6,000 years to count to 200 billion. And that is just the stars. Around those stars orbit trillions of planets, moons, asteroids, and comets. The galaxy spans roughly 100,000 light-years from edge to edge. Light itself, the fastest thing in the universe, takes 100 millennia to cross from one side to the other. A Type 3 civilization would have spread across all of this, not as scattered outposts maintaining tenuous contact with a distant homeworld, but as an integrated civilization with the entire galaxy as its domain. The energy at their disposal would be on the order of 10 to the power of 36 watts, approximately 10 billion times greater than a Type 2 civilization, and 100 trillion times greater than current human civilization. These are not numbers that the human mind can intuitively grasp. They are more like coordinates marking a location in conceptual space, pointing towards something real but fundamentally alien to our everyday experience. How would such a civilization come to exist? The answer requires us to think on timescales that dwarf human history entirely. Even with near-light speed travel, colonizing a galaxy would take tens of thousands of years at minimum. But if we assume that colonization proceeds through a process of expansion, with each new stellar system sending out its own colony ships to nearby stars, the math becomes more tractable. This process, sometimes called a von Neumann colonization wave after the mathematician who first analysed self-replicating machines, could sweep across an entire galaxy in remarkably little time by cosmic standards, perhaps 1 to 10 million years depending on the speed of the ships and the time required to establish each new colony. 10 million years sounds like an eternity from a human perspective. It is enough time for entire species to evolve and go extinct. It is longer than the time since our ancestors first walked upright on the African savanna. But from a cosmic perspective, 10 million years is an eye blink. The universe is nearly 14 billion years old. Galaxies formed more than 13 billion years ago. If intelligent life arose anywhere in the Milky Way even a few 100 million years before Earth, they would have had more than enough time to colonize the entire galaxy many times over. This is the core of the Fermi paradox, and at the Type 3 level it becomes truly acute. If galactic colonization is possible, and if it takes only millions of years to accomplish, and if the galaxy is billions of years old, then where is everyone? Why does the galaxy not show obvious signs of engineering and habitation? Why do we see natural stellar systems rather than the orderly arrangements we might expect from beings who reshape reality to suit their purposes? The question becomes even more pressing when we consider what a Type 3 civilization's activities might look like from afar. Their energy harvesting infrastructure would surround billions of stars. The collective waste heat from their activities would alter the infrared signature of the entire galaxy. They might rearrange stellar orbits to optimize for energy collection or resource extraction. They might have constructed communication networks that span the entire galactic disk. The galaxy should look different. It should look managed. Yet by all appearances it looks wild. Several possible explanations have been proposed, and each one reveals something important about our assumptions and limitations. The first explanation is simply that Type 3 civilizations do not exist, because the Great Filter prevents anyone from reaching that level. Perhaps the transition from Type 2 to Type 3 is where civilizations consistently fail. A Type 2 civilization, as mentioned before, possesses technologies of enormous destructive potential. Perhaps internal conflicts or accidents consistently destroy civilizations before they can spread beyond their home stellar system. Perhaps the Lotus Eater trap is real, and civilizations consistently choose comfortable stagnation over the difficult project of galactic expansion. Perhaps something else entirely, some risk we have not yet conceived, awaits at that stage of development. The second explanation is that Type 3 civilizations exist, but are invisible to us for reasons we do not understand. Perhaps they have transcended physical existence entirely, uploading their minds into computational substrates that operate on principles we cannot detect. Perhaps they have migrated to other dimensions or other planes of existence that physics has not yet revealed to us. Perhaps they are hiding deliberately, either because they consider it impolite to interfere with developing civilizations, or because the galaxy is a dangerous place where visibility means vulnerability. This second possibility connects to what is sometimes called the dark forest hypothesis. named after a science fiction novel by the Chinese author Liu Cixin. The idea is that the galaxy might be hostile, filled with civilizations that destroy any other civilization they detect as a precautionary measure. In such an environment, the optimal strategy for survival would be perfect silence and perfect invisibility. A Type 3 civilization that had survived for millions of years would have learned this lesson and would take extraordinary measures to avoid detection. If the dark forest hypothesis is correct, the silence of the cosmos is not evidence that advanced civilizations are absent. It is evidence that advanced civilizations are wise. They have learned that broadcasting your presence is suicidal. They have learned that the only way to survive in a galaxy full of potential competitors is to be seen by no one. The universe is not empty. It is a forest at night, full of hidden predators listening in the darkness. The third explanation, and perhaps the most unsettling, is that Type 3 civilizations exist and are present in our own galaxy, but we are simply unable to perceive them. Consider the cognitive gap between humans and ants. An ant colony might exist directly beneath a human city, completely unaware of the civilization above it. The ants cannot perceive skyscrapers or automobiles or the internet. These things operate on scales and at speeds entirely outside the ant's sensory and cognitive capabilities. The ants are not stupid within their own domain. They have their own complex social structures, their own engineering projects, their own forms of communication. But they are blind to the larger world that surrounds them. We might be in exactly this position with respect to Type 3 civilizations. Their activities might be occurring all around us, woven into the fabric of reality in ways our science has not yet learned to detect. The orderly patterns we might expect to see in a managed galaxy might be present at scales or frequencies or dimensions we have not thought to examine. We look at the sky and see stars and space, but perhaps we are like the ant looking up through a crack in the sidewalk, perceiving only a tiny fragment of a reality that extends far beyond our comprehension. This is a deeply uncomfortable idea for a species that prides itself on scientific understanding. We have mapped the cosmos from the cosmic microwave background to the most distant galaxies. We have probed the structure of matter from atoms down to quarks. We have developed theories that accurately predict phenomena across dozens of orders of magnitude. Surely if Type 3 civilizations were present, we would have noticed something by now. Surely our instruments would have detected some anomaly that pointed toward their existence. But confidence in our scientific completeness might be premature. Consider how much our understanding of the universe has changed in just the past few decades. Dark matter and dark energy, which together make up 95% of the universe's mass-energy content, were unknown a generation ago. Gravitational waves, predicted by Einstein over a century ago, were only directly detected in 2015. Exoplanets, now known to be ubiquitous, were purely theoretical until the 1990s. Our scientific picture of the cosmos is still actively evolving. There may be entire categories of phenomena we have not yet begun to investigate. Let us now turn from these cosmic speculations to something more concrete. What would the actual experience of existing in a Type 3 civilization be like? Here we must acknowledge that any answer we give will be highly speculative. The gap between our current existence and existence at that level is so vast that meaningful comparison becomes almost impossible. But we can make some educated guesses based on extrapolation from trends we already observe. First, the concept of individual identity might be radically transformed. In a civilization spanning billions of stars, communication delays would be measured in years or centuries. A being on one side of the galaxy could not have a real-time conversation with a being on the other side. This suggests that either such a civilization would fragment into effectively independent sub-civilizations, or they would have developed technologies that transcend the limitations of light-speed communication. Perhaps consciousness could be copied and transmitted, allowing a single identity to exist simultaneously in multiple locations. Perhaps time itself could be manipulated, making the vast distances irrelevant. Second, the boundary between natural and artificial might disappear entirely. A Type 3 civilization would have been engineering their environment for millions of years. The stars themselves might be managed resources, their evolution guided by deliberate intervention. Planets might be constructed to specification rather than evolved through natural processes. Life forms might be designed rather than evolved. At some point, the distinction between what is natural and what is technological becomes meaningless. Everything is engineered. Everything is artificial. or equivalently, everything is natural, including the engineering that created it. Third, the relationship between physical and virtual existence might be inverted. For a civilization with effectively unlimited computational resources, simulated realities could be created at any level of fidelity desired. These simulations might be indistinguishable from physical reality to their inhabitants. Indeed, they might be preferred to physical reality, offering experiences and possibilities that the physical universe cannot provide. A Type 3 civilization might consist primarily of minds existing in simulated environments, with physical infrastructure maintained only as the substrate that runs the simulations. This brings us to a fascinating and disturbing possibility that has received increasing attention from scientists and philosophers alike. If Type 3 civilizations routinely create simulated realities, and if those simulated realities contain conscious beings who believe themselves to be living in a physical universe, then the number of simulated beings in the cosmos would vastly exceed the number of physical beings. By simple statistical reasoning, any randomly chosen conscious entity is far more likely to be simulated than physical. This is the simulation hypothesis, and it suggests that we ourselves might be inhabitants of a simulation created by a Type 3 civilization. The idea sounds like science fiction, but it has been taken seriously by respected philosophers like Nick Bostrom, who formulated the argument rigorously in 2003. Bostrom argued that one of three propositions must be true. Either civilizations consistently destroy themselves before achieving the capability to run detailed simulations of conscious beings, or civilizations with that capability consistently choose not to run such simulations, or we are almost certainly living in a simulation right now. The logic is straightforward. If simulations are created, their inhabitants vastly outnumber physical beings, and we have no way to know from the inside which kind of being we are. Recently, however, physicists have begun to push back against this reasoning. A paper published in early 2025 by Franco Vazza at the University of Bologna examined the physical constraints on simulating a universe like ours. The conclusions were striking. Simulating the entire observable universe in full physical detail would require more energy than exists in the observable universe. Simulating just the Earth would still require astronomical amounts of energy, far exceeding what even a Type 3 civilization might plausibly deploy for such a purpose. Even a low-resolution simulation consistent with our observations of high-energy cosmic rays would push against fundamental physical limits. This does not definitively refute the simulation hypothesis. Perhaps we are in a simulation that does not aim for full physical fidelity. Perhaps computational shortcuts we cannot conceive make simulation easier than our physics suggests. Perhaps the simulators exist in a reality with different physical laws where the calculations are more tractable. But it does suggest that the simulation hypothesis faces serious objections from physics, not just philosophy. What matters for our present purpose is that these are the kinds of questions that become relevant when we contemplate civilizations at the Type 3 level. We are no longer talking about better rockets or more efficient power plants. We are talking about the fundamental nature of reality, consciousness, and existence. The Kardashev Scale, which began as a simple measure of energy consumption, leads us inexorably toward the deepest questions that any intelligent being can ask. And remarkably, the scale does not stop at Type 3. Some theorists have extended the framework even further, proposing Type 4 civilizations that harness the energy of an entire universe. Type 5 civilizations that span multiple universes in a multiverse and beyond. As we ascend these levels, we leave behind any pretense of engineering or technology. We enter realms that might better be described as metaphysics or theology. We ask what it means for intelligence to approach the limits of existence itself. But before we climb those vertiginous heights, we must return to more immediate concerns. The journey from Type 0 to Type 3 is not just an abstract progression. It is a series of trials that must be survived. Each transition carries risks. Each advancement offers new ways to fail. The Great Filter, which we have discussed throughout this exploration, might lurk at any of these transitions, ready to claim civilizations that reach for power beyond their wisdom. Understanding these filters, mapping the dangers that lie ahead, is not just an academic exercise. It is potentially a matter of survival. Because if we know where the filters are, we might be able to navigate around them. If we understand what destroyed other civilizations, we might be able to avoid their fate. The Kardashev Scale is not just a measure of achievement. It is a map of the minefields we must cross to claim our place among the stars, the gauntlet of extinction. Every civilization that has ever looked up at the stars and wondered has faced the same fundamental question. Will we survive long enough to join them? Will we thread the needle between ambition and annihilation, between the power to reshape worlds and the wisdom to avoid destroying ourselves? This question is not new. It has been asked since the first human societies developed weapons capable of mass destruction. But in our era, the question takes on a new urgency because we can now enumerate, with disturbing precision, the specific threats most likely to end our story before it truly begins. The concept of the Great Filter provides a framework for thinking about these threats systematically. Somewhere in the journey from lifeless chemistry to galaxy-spanning civilization, there exists a barrier or series of barriers that most intelligent species never cross. The filter might be behind us, in which case we are extraordinarily fortunate to exist at all. Or the filter might be ahead of us, in which case our future is far more precarious than our present comfort suggests. For many years, scientists debated where the filter might be located. Was it the origin of life itself, the improbable leap from dead matter to self-replicating molecules? Was it the evolution of complex cells, the merger of simpler organisms that gave rise to the eukaryotes from which all complex life descends? Was it the development of intelligence, the emergence of minds capable of abstract thought and technological creation? Each of these transitions is improbable enough that it might explain the silence of the cosmos. But increasingly, researchers are focusing on a different possibility. The filter might not be a natural barrier at all. It might be a self-inflicted wound, a trap that technological civilizations set for themselves. It might be something we are actively constructing with each passing year. The paper published by Michael Garrett in April of 2024 laid out this case with disturbing clarity. Garrett, one of the world's leading astrophysicists and a central figure in the search for extraterrestrial intelligence, proposed that artificial intelligence might be the great filter. His argument proceeds through several stages, each building on the last to construct a picture of civilizational risk that demands our attention. The first stage of the argument notes that any civilization advanced enough to develop radio technology will inevitably develop computing technology as well. This is not a cultural choice, but a technological inevitability. The same intellectual capabilities that allow a species to understand electromagnetic radiation will allow them to understand logic gates and information processing. Once a civilization has computing, the drive toward artificial intelligence follows almost automatically from the desire to automate, to optimize, to create tools that extend mental capabilities. The second stage observes that artificial intelligence improves at rates that biological evolution cannot match. Our brains are the product of millions of years of gradual refinement. AI systems double their capabilities in months or years. There is no biological mechanism that can keep pace with this rate of change. At some point, perhaps soon, perhaps already past, AI systems will become capable of improving themselves. When that happens, the rate of progress becomes exponential in a way that leaves biological intelligence helplessly behind. The third stage considers what happens when this gap becomes unbridgeable. An artificial superintelligence would think faster than we do, see patterns we cannot perceive, formulate plans we cannot understand. If its goals are not perfectly aligned with human flourishing, and ensuring such alignment is an unsolved problem despite decades of research, then the outcomes could be catastrophic. We would be in the position of chimpanzees trying to negotiate with humans, or more precisely, in the position of chimpanzees whose fate depends on humans deciding to take their interests into account. Garrett's paper estimates that the average lifespan of a technological civilization might be less than 200 years from the development of radio technology to extinction or fundamental transformation. This is not a number plucked from thin air. It is derived from considering the pace of AI development, the difficulty of alignment, and the various ways that advanced AI might threaten or terminate biological civilization. If this estimate is correct, it explains elegantly why we have not detected signals from other civilizations. They are not out there because they did not survive long enough. But artificial intelligence is not the only threat we face. It is perhaps the most novel and therefore the most difficult to evaluate. But there are older dangers, ones we have lived with for decades, that remain potent even as we focus on newer risks. Nuclear weapons have threatened human civilization since 1945. For 8 decades, we have lived in the shadow of potential annihilation, deterred from the ultimate catastrophe only by the logic of mutually assured destruction. This logic has held so far. There have been close calls, moments when miscalculation or accident nearly triggered exchanges that would have devastated the planet. But so far we have stepped back from the brink each time, yet deterrence is not stability. It is a tense equilibrium that could be disrupted by any number of developments. The spread of nuclear weapons to additional states increases the number of fingers on the trigger. The development of missile defense systems threatens to undermine the logic of assured destruction that has kept the peace. The integration of artificial intelligence into command and control systems introduces new uncertainties about how quickly decisions might escalate beyond human control. The nuclear danger is often treated as a solved problem, a relic of the Cold War that no longer demands our urgent attention. This is a dangerous complacency. The weapons still exist. The launch systems are still operational. The potential for catastrophic miscalculation remains. As long as nuclear arsenals sufficient to end civilization persist, the filter they represent has not been passed. It has merely been delayed. Climate change represents a slower moving but equally profound threat. Unlike nuclear war, which would destroy through sudden violence, climate disruption kills through gradual degradation. Rising temperatures, shifting weather patterns, failing ecosystems, mass migrations driven by environmental collapse, these are not scenarios from speculative fiction, but trends already underway, measurable in data collected from around the world. The challenge with climate change is that its timescales do not match human psychology. We evolved to respond to immediate threats, saber-toothed tigers and rival tribes, not gradual changes that unfold over decades. Politicians work on electoral cycles measured in years. Businesses focus on quarterly earnings. The climate system operates on timescales of centuries and millennia. This mismatch creates a systematic bias toward inaction, toward postponing difficult decisions until the consequences become impossible to ignore, by which point they may also be impossible to reverse. A Type 1 civilization would solve the climate problem essentially as a byproduct of its energy transition. With unlimited clean energy from fusion and renewables, with the capability to actively manage atmospheric composition, with resources sufficient to relocate populations and rebuild infrastructure as needed, climate change would cease to be an existential threat. But we are not yet a Type 1 civilization. We are a Type 0.7 something, still burning fossil fuels and still pumping carbon into the atmosphere, still debating whether the problem is real even as its effects accumulate around us. Pandemics represent another category of risk, one that the recent past has made viscerally real. The global spread of infectious disease is not new, but our interconnected world makes it faster and harder to contain. A pathogen emerging in one city can circle the globe within weeks. The same transportation networks that enable trade and travel also enable viral spread. And advances in biotechnology create new possibilities for pathogens that are deliberately engineered rather than naturally evolved. The dual-use nature of biological knowledge creates a particularly vexing problem. The same technologies that allow us to develop vaccines and treatments also allow us to create novel pathogens. The same sequencing capabilities that let us understand viruses also let us synthesize them. As these technologies become more accessible, the pool of individuals and groups capable of creating biological weapons expands. We are democratizing the capability for mass casualties. Each of these risks, AI, nuclear weapons, climate change, pandemics, operates on a different timescale and requires different interventions. But they share a common structure. They are all products of technological progress outpacing social wisdom. They are all consequences of developing capabilities faster than we develop the institutions and norms needed to manage those capabilities safely. They are all expressions of the fundamental tension that defines our era, the gap between our power and our maturity. This is the essence of the great filter as it applies to us. We have become capable of destroying ourselves before we have become wise enough to avoid doing so. We can split atoms and edit genes and create thinking machines, but we cannot agree on how to manage these capabilities for the common good. We can see the risks clearly, enumerate them precisely, model their potential consequences, but we cannot summon the collective will to address them decisively. The question that haunts researchers who study existential risk is whether this is an intrinsic feature of technological civilizations, or just a contingent feature of ours? Is the gap between capability and wisdom a necessary consequence of how technology develops? Or is it specific to human history, a product of our particular evolutionary heritage and social structures? If the gap is intrinsic, then the great filter is ahead of every civilization. Every species that develops advanced technology will face a period of existential vulnerability when their power exceeds their wisdom. Most will not survive this period. The silence of the cosmos would be explained by the reliable self-destruction of technological civilizations, not through malice, but through the inevitable mismatch between what they can do and what they can control. If the gap is contingent, then hope remains. Perhaps we can accelerate the development of wisdom to match our development of capability. Perhaps we can create institutions robust enough to manage existential risks. Perhaps we can extend our moral circle to include future generations and ensure that their interests are considered in present decisions. The filter might be real, but it might be navigable. We might be the civilization that finds the path through. This is where the concept of civilizational resilience becomes crucial. If we cannot prevent existential risks entirely, we can at least reduce our vulnerability to them. The most obvious form of resilience is becoming a multiplanetary species. A civilization that exists on multiple worlds cannot be eliminated by any catastrophe limited to a single planet. If asteroid impact or nuclear war or pandemic disease devastates Earth, settlements on Mars or in space habitats could continue. The species would survive even if any particular world did not. This is the logic driving SpaceX's Mars colonization program, which we touched on earlier. When Elon Musk talks about making life multiplanetary, he is not just pursuing adventure or profit. He is pursuing civilizational insurance. He is trying to ensure that whatever mistakes we make on Earth, whatever filters we fail to pass, there will be a backup, a second chance, a continuation of the human story even if the first chapter ends badly. The May 2025 presentation at Starbase laid out a roadmap with specific milestones: uncrewed Starship landings on Mars by late 2026, human missions as early as 2028 or more conservatively 2031, a self-sustaining colony of 1 million people by 2050. These are aggressive timelines, and they may slip, but they represent a serious attempt to achieve the one thing that could reduce our existential vulnerability more than any other single intervention. But resilience alone is not enough. We also need to reduce the risks themselves, not just survive them. This requires developing technologies safely rather than recklessly, building institutions that can govern powerful capabilities effectively, and cultivating the social cohesion needed for collective action on global challenges. In the case of artificial intelligence, this means investing heavily in alignment research, the technical work of ensuring that AI systems pursue goals that are beneficial to humans. It means developing governance frameworks that can adapt as AI capabilities advance. It means fostering international cooperation to prevent races to the bottom, where safety is sacrificed for competitive advantage. The field is young and the problems are hard, but they are not impossible. We have time, perhaps not much, but enough if we use it wisely. In the case of nuclear weapons, progress requires reductions in arsenals, improvements in command and control to prevent accidental launch, and ultimately movement toward a world where these weapons no longer exist. This is a goal that seemed more achievable during the optimistic years after the Cold War than it does today. Geopolitical tensions have risen. Arms control agreements have frayed or collapsed. But the goal remains valid even if the path to it has become more difficult. In the case of climate change, the technology needed to solve the problem largely exists. Solar and wind power are now cheaper than fossil fuels in many contexts. Electric vehicles are rapidly displacing internal combustion engines. Battery storage is improving year over year. The challenge is deployment, building the clean energy infrastructure fast enough to matter, and overcoming the political and economic obstacles that entrench fossil fuel interests. This is a race against time, that we could still win if we chose to treat it with the urgency it deserves. The great filter is not a fixed barrier, but a probability distribution. Some civilizations pass it, some do not. Where we fall on that distribution depends on choices we make in the coming decades. Every investment in AI safety shifts the probability in our favor. Every reduction in nuclear arsenals improves our odds. Every solar panel installed and every ton of carbon captured makes our passage more likely. We are not helpless before the filter. We are active participants in determining whether we pass through. This is perhaps the most important takeaway from studying the Kardashev Scale and the risks associated with ascending it. The future is not determined. It is not written in advance by laws of physics or historical necessity. It emerges from the accumulated choices of billions of individuals, institutions, and nations. We are the ones who will decide whether humanity reaches the stars or ends its story here on Earth. The responsibility is ours, and it is absolute. As we turn now to the higher levels of the Kardashev Scale, to Type 4 and beyond, we enter realms so speculative that they approach philosophy more than science. But there is value in contemplating these possibilities, even if we may never reach them. They reveal what might be possible for intelligence in the universe. They suggest destinations toward which we might aspire. And they remind us that the journey we have barely begun could lead to places more wonderful than anything we have yet imagined. Beyond the galaxy, when Nikolai Kardashev first proposed his scale in 1964, he stopped at Type 3. A civilization that had harnessed the energy of an entire galaxy seemed so far beyond any plausible human achievement that extending the scale further would have been pure fantasy. But in the decades since, theorists have dared to ask what might lie beyond galactic civilization. If intelligence can grow to command the resources of 100 billion stars, why should it stop there? Why not imagine intelligence that spans clusters of galaxies, then superclusters, then the observable universe itself? Why not imagine intelligence that transcends the boundaries of our universe entirely and reaches into the multiverse that some physicists believe contains infinite alternate realities? These extensions of the Kardashev Scale, Type 4 through Type 7, take us into territory so speculative that the line between science and philosophy, between physics and metaphysics, becomes impossible to draw with confidence. But speculation is not worthless. It helps us understand the ultimate limits of what intelligence might achieve. It provides a framework for thinking about possibilities so vast that without such a framework our minds would simply refuse to engage with them. And it reveals something important about the nature of progress itself, about where the trajectory we have begun might eventually lead. A Type 4 civilization, in most formulations, is one that has achieved control over the energy output of an entire universe. Not a galaxy, but a universe. All the galaxies, all the stars, all the matter and energy contained within the observable cosmos. The numbers involved beggar comprehension. The observable universe contains approximately 2 trillion galaxies. If each galaxy contains roughly 200 billion stars, the total number of stars exceeds 4 times 10 to the power of 23. That is 400 sextillion stars. A Type 4 civilization would be drawing energy from all of them. How could such a civilization come to exist? The most straightforward path would be through continued expansion at the galactic level. A Type 3 civilization that had colonized its home galaxy might send expeditions to nearby galaxies. The distances are vast, measured in millions of light-years rather than the tens of thousands of light-years that span a single galaxy. The journey times, even at significant fractions of light speed, would be measured in millions of years. But time, for a civilization that has already existed for millions of years, might be no obstacle at all. The Andromeda Galaxy, our nearest large neighbour, is about 2.5 million light-years away. A colony ship travelling at 10% of light speed would take 25 million years to arrive. This seems impossibly long by human standards, but a Type 3 civilization might think nothing of it. They might send thousands of such ships, each carrying the seeds of new civilizations that would themselves grow to Type 3 status and send out their own expeditions. The pattern would replicate itself across intergalactic space, a wave of colonization spreading through the universe at some fraction of light speed. Over billions of years, this process could fill the observable universe with intelligent activity. Every galaxy would be colonized, every star would be harnessed, every resource would be put to use. The universe would no longer be a natural phenomenon but an engineered one, shaped entirely by the purposes of the intelligence that had spread to fill it. But there is a catch, and it is a significant one. The universe is expanding. Not only is it expanding, but the expansion is accelerating due to dark energy. the mysterious force that constitutes about 68% of the universe's total content. Distant galaxies are receding from us at speeds proportional to their distance. Galaxies beyond a certain threshold are receding faster than light itself can travel, not because they are moving through space faster than light, which would violate relativity, but because the space between us and them is expanding at such a rate. This means there is a cosmic horizon beyond which we can never reach, no matter how fast we travel or how long we wait. The observable universe will become increasingly isolated over cosmic time. Galaxies that are currently visible will eventually disappear over the horizon, lost to us forever. A Type 4 civilization would face this limit. They could colonize everything within reach, but they could never colonize everything that exists. The universe might be infinite, but the accessible universe is finite and shrinking. Perhaps this does not matter for practical purposes. The accessible universe still contains trillions of galaxies and sextillions of stars. Even a civilization that exists for trillions of years would not exhaust these resources. But it does suggest that Type 4 might be an asymptotic limit, rather than a fully achievable state. A civilization might approach universal dominance without ever quite reaching it. What would existence be like at this level? The concept of individual identity would almost certainly be unrecognizable to us. A civilization spanning trillions of galaxies would face communication delays measured in millions of years. No central coordination would be possible in any meaningful sense. Each region would necessarily be autonomous, making its own decisions, developing its own culture, perhaps even diverging into effectively separate species or forms of intelligence. What began as a single civilization would become a tapestry of countless sub-civilizations, linked by common origin, but separated by gulfs of space and time that no signal could bridge in less than geological ages. Perhaps the solution would be to abandon individuality entirely. Instead of distinct beings communicating across vast distances, perhaps a Type 4 civilization would consist of a single distributed consciousness, a mind that spans the universe and experiences all of its parts simultaneously. This is a concept that stretches our ability to imagine, but it is not obviously impossible. If consciousness is ultimately a pattern of information processing, and if that processing can be distributed across any substrate, then a universe-spanning mind might be as real as the individual minds we experience ourselves to possess. Such a mind would think on timescales measured in millions or billions of years. It would make decisions that unfold across cosmic epochs. Its thoughts would be carried by signals travelling at the speed of light, the fastest possible transmission in our physics. From our perspective, it would appear to be moving impossibly slowly, but from its own perspective, it might experience time quite differently. Perhaps a billion years of objective time would feel like a moment of subjective experience. Perhaps the apparent slowness is an illusion born of our limited frame of reference. Now we must take another step into the speculative unknown. Type 5. Civilizations, in most formulations, transcend our universe entirely. They operate at the level of the multiverse, the collection of all possible universes that some physical theories predict to exist. The multiverse is a controversial concept among physicists. Some theories, particularly certain interpretations of quantum mechanics and certain versions of cosmic inflation, suggest that our universe is just one of an enormous, perhaps infinite, number of universes. These universes might have different physical constants, different laws of physics, different initial conditions. Some might be hospitable to life, others sterile, some might be similar to ours, others radically different in ways we cannot imagine. If the multiverse exists, and if it is possible to travel between universes or at least to access the resources of other universes, then a Type 5 civilization would be defined by its mastery of this trans-universal domain. It would not be limited to the energy output of a single universe, but could draw on the resources of countless universes. It would not be constrained by the physical laws of any particular universe, but could select universes with laws favourable to its purposes, or perhaps even create new universes to specification. This is deeply speculative. We do not know if the multiverse exists. We do not know if travel between universes is possible. We do not know if the concept of energy even translates across universes with different physical laws. But the speculation is valuable because it pushes us to consider the limits of physical existence. If intelligence can transcend the constraints of a single universe, what ultimate limits does it face? If the multiverse is infinite, Is there any ceiling on what intelligence might achieve? Some theorists suggest that the answer is no. A Type 6 civilization, in these formulations, would operate at the level of the fundamental laws of reality itself. They would not merely exploit existing physical laws, but would create new ones. They would be architects of reality, designers of the stage on which all existence plays out. The distinction between natural and artificial would be meaningless at this level, because nature itself would be their creation. A Type 7 civilization, if such a concept even makes sense, would transcend all categories we can formulate. They would not be within reality, but would be reality, or perhaps the source from which reality emerges. They would be what theologians have traditionally called God, not in the sense of a supernatural being, but in the sense of an ultimate ground of existence, a necessary foundation upon which everything else depends. Here we have clearly crossed from physics into philosophy, perhaps even into theology. But this is instructive. The Kardashev Scale, which began as a practical tool for thinking about the energy consumption of civilizations, leads us inexorably toward the deepest questions human minds have ever asked. What is the nature of reality? What is the ultimate origin of existence? What might intelligence become if it had infinite time and infinite resources? These questions have occupied philosophers and mystics for thousands of years. They appear in every human culture, expressed in the languages and symbols available to each. The idea that intelligence might grow until it encompasses all reality is not new, it is ancient. What is new is the scientific framework that allows us to approach these questions rigorously, to ask what physics permits and what physics forbids, to ground our speculations in the actual structure of the universe rather than mere imagination. But we must be careful not to lose ourselves in speculations so remote from our current situation that it becomes a distraction from more immediate concerns. Type 4 through Type 7. Civilizations are not just far away in time, they are far away in the chain of causation that connects the present to any possible future. Before we can contemplate universal dominance, we must survive the next few centuries. Before we can engineer reality, we must learn to manage our own planet. Before we can become gods, we must first become Type 1. There is a tendency in futurism to leap over the difficult middle stages, to imagine the glorious destination while ignoring the treacherous journey required to reach it. This is a mistake. The journey is where the real challenges lie. The journey is where civilizations succeed or fail. And the journey, for us, has barely begun. The higher levels of the Kardashev Scale serve a different function than the lower levels. They are not roadmaps for the next few centuries. They are visions of ultimate possibility, destinations toward which the entire trajectory of cosmic intelligence might lead. They remind us that the stakes of what we are doing now extend far beyond our immediate concerns. If we succeed in passing through the Great Filter, if we manage to become a multi-planetary species and then a stellar species and then a galactic species, we are not just ensuring our own survival, we are potentially launching a wave of intelligence that might eventually encompass the universe. This is either the most magnificent destiny imaginable or the most terrifying responsibility. Perhaps both. We are right now, in this moment, the custodians of possibilities so vast that they exceed our capacity to grasp them fully. Every choice we make, every investment we prioritize, every risk we take or avoid, ripples forward into a future that might contain Type 4 civilizations or might contain nothing but silent stars and empty worlds. The higher Kardashev levels also serve to put our current struggles in perspective. The political conflicts that dominate our news, the economic anxieties that preoccupy our thoughts, the social divisions that tear at our societies, these are real and they matter. But from the perspective of cosmic evolution, they are local phenomena, temporary obstacles on a path that extends far beyond anything they could obstruct. The ultimate enemy is not any particular ideology or nation or interest group. The ultimate enemy is extinction itself, the closing of all paths forward, the termination of all possibilities. When we argue about climate policy or AI regulation or space funding, we are not just arguing about economics or politics. We are arguing about whether the human story continues or ends. We are arguing about whether intelligence spreads beyond this one fragile planet or remains forever confined here, waiting for the inevitable asteroid or supervolcano or gamma-ray burst that will sterilize the only world we have ever known. This perspective does not tell us which policies to choose. Reasonable people can disagree about means even when they agree about ends, but it does suggest that the ends are far more important than our everyday discourse typically acknowledges. The future of intelligence in the universe might depend on decisions being made right now, by people alive today, about things that seem mundane but carry cosmic significance. With that weight upon us, let us continue our exploration. We have climbed from Type 0 to the theoretical heights of Type 7. Now we must return to the puzzle that motivated this entire investigation. If intelligence can grow to such heights, if the journey from microbe to universal mind is possible, then why do we see no evidence of it when we look at the sky? The Fermi paradox remains our constant companion, and it demands an accounting. Perhaps in seeking to explain the silence, we will discover something essential about our own place in the cosmos. The architecture of existence. There is a point in any ascending journey where the path ceases to be about reaching higher ground, and becomes instead about transforming into something capable of perceiving what higher ground means. A mountain climber approaching the summit faces physical challenges, thin air and cold and exhaustion. But an intelligence approaching the uppermost reaches of the Kardashev Scale faces something more fundamental. It faces the limits of what intelligence itself can be. And perhaps, at the very highest levels, it faces the dissolution of the boundary between the intelligence that observes and the reality it observes. Type 6 and Type 7 civilizations, as conceptualized by those who have extended the Kardashev framework to its theoretical limits, are not really civilizations at all in any sense we would recognize. They are not collections of individuals cooperating toward shared goals. They are not societies with cultures and histories and internal dynamics. They are something else entirely. They are intelligence that has merged so completely with reality that the distinction between creator and creation no longer applies. A Type 6 civilization, in these formulations, would have mastery over the fundamental laws of physics themselves, not merely exploiting the laws that happen to exist, as a Type 5 civilization might do by navigating between universes with different physics, but actually writing the laws, determining what is possible and what is not, choosing the values of fundamental constants, designing the mathematical structures that constrain how matter and energy behave. This is a staggering concept. The laws of physics, as we understand them, are not arbitrary. They are not chosen. They are discovered. We probe nature through experiment and theory, gradually uncovering principles that seem to be woven into the fabric of existence itself. The speed of light is what it is. The charge of an electron is what it is. The gravitational constant has the value it has. These are not parameters we set, but facts we find. Yet the suggestion from theoretical physics, particularly from certain approaches to cosmology and quantum gravity, is that our universe's physical laws might be contingent rather than necessary. They might be features of this particular universe rather than features of all possible realities. If the multiverse exists, there might be other universes with different laws, different constants, different possibilities. And if laws can vary between universes, then perhaps, for sufficiently advanced intelligence, they can be chosen. How would one go about designing physical laws? The question stretches beyond anything we can currently imagine. Our physics describes how the universe works given its laws, not how to change those laws. We have no theory of metaphysics in the literal sense, no understanding of what determines the laws themselves. But the absence of understanding today does not mean the absence of possibility tomorrow. A Type 3 civilization would possess knowledge that seems magical to us. A Type 6 civilization would possess knowledge that seems impossible. Perhaps the answer lies in the mathematical structures that underlie physical reality. Contemporary physics increasingly suggest that the universe is, at its deepest level, mathematical. The entities we call particles and forces and fields are, on close examination, mathematical objects obeying mathematical relationships. Space itself may be emergent from more fundamental mathematical structure. Time may be similarly derivative. If reality is mathematics, then designing reality might be a matter of choosing which mathematical structures to instantiate. This perspective finds expression in what some theorists call the mathematical universe hypothesis, proposed by physicist Max Tegmark. According to this view, every mathematically consistent structure exists as a physical reality somewhere in the ultimate ensemble of all possible universes. Our universe corresponds to one particular mathematical structure among infinitely many. A Type 6 civilization in this framework would not be creating mathematical structures but navigating among them, selecting which ones to inhabit or connect to, effectively choosing its own physics by choosing its location in the space of all possible mathematics. But let us push further still. Type 7, in the most extreme formulations, transcends even this. A Type 7 civilization would not be within the space of mathematical possibilities. It would be that space. It would not be an observer or manipulator of reality. It would be reality itself, or the source from which reality flows. Here we have arrived at territory that theologians and mystics have explored for millennia, using different vocabularies. The concept of an ultimate ground of existence, a necessary being from which all contingent beings derive, appears in nearly every philosophical and religious tradition. In Western philosophy, it takes the form of Aristotle's unmoved mover, or Aquinas' necessary being. In Eastern traditions, it appears as Brahman, the ultimate reality underlying all phenomena, or as the Tao, the unnameable source of everything that exists. In monotheistic religions, it is God, the creator and sustainer of all that is. The Kardashev Scale, pushed to its limit, converges on these ancient intuitions. If intelligence can grow without limit, if it can transcend galaxy and universe and multiverse, then its ultimate destination might be something that the religious traditions have pointed toward all along. Not a supernatural being in some other realm, but the natural culmination of intelligence evolving within the physical universe, growing until it becomes indistinguishable from the creative principle that theologians call divine. This is not to say that theology has been doing physics all along, or that physics validates any particular religious doctrine. The convergence is at the level of the question, not the answer. Both science and religion ask what lies at the foundation of existence. Both attempt to understand the relationship between intelligence and reality. Both grapple with the possibility that consciousness might be more fundamental than matter, or that the universe might exist for a purpose, or that the distinction between mind and world might be less absolute than it appears. What science brings to these questions is a methodology, a way of testing ideas against evidence and refining them through experiment. What the extension of the Kardashev Scale offers is a framework for thinking about how intelligence might actually evolve towards states that philosophy and religion have long imagined. The synthesis is incomplete and tentative, but it suggests that the deepest questions are not going away as science advances. They are becoming more pressing, more immediate, more relevant to understanding our situation. Let us now consider what existence might be like, if the word existence even applies, at these rarefied levels. A Type 7 being, if we can call it a being, would not experience reality the way we do. It would not have a perspective within reality from which it observes other things. It would not have needs or desires in any sense we would recognize. It would not act upon a world separate from itself because there would be no such separation. Perhaps the closest analogy we can offer is dreaming. In a dream, the dreamer and the dream are not truly separate. The dreamer creates the dreamscape, populates it with characters, generates events and narratives, all while experiencing the dream from within. There is an observer and an observed, but they are both aspects of the same underlying reality, the sleeping mind. A Type 7 existence might be something like a dream from which there is no waking, a creative unfolding that is both the dreamer and the dreamed, both the story and the storyteller. This analogy has its limits, of course. Human dreams are fragmentary, inconsistent, forgotten upon waking. A Type 7 existence would presumably lack these limitations. It would be a dream of perfect coherence, infinite scope, and eternal duration. But the basic structure might be similar. The distinction between subject and object, between self and other, might be a feature of lower-level existence that dissolves at the highest levels. If this sounds mystical, that is because it is. We have travelled beyond the boundaries of what current science can illuminate. We are speculating about possibilities that no experiment can test, no observation can confirm. This is the nature of ultimate questions. They exceed our current methods. They invite contemplation rather than measurement. But the speculation is not pointless. It orients us. It tells us what kinds of questions matter and what kinds of answers might ultimately satisfy. It prevents us from assuming that our current understanding is complete, that physics as we know it captures everything there is to capture, that the universe exhausts the realm of possibility. And it brings us back, surprisingly, to our own situation. Because if the trajectory of intelligence leads towards states that approach the divine, then every step on that trajectory has significance beyond itself. We are not just surviving, we are not just prospering, we are participating in a cosmic process that might end somewhere unimaginably wonderful, or might end nowhere at all if we fail to navigate the challenges immediately before us. The Kardashev Scale, viewed in this light, is not just a measure of energy consumption, it is a measure of proximity to something ultimate. Each level brings us closer to understanding what reality is, and what our place in it might be. Each transition tests our wisdom as well as our technology. Each success opens possibilities that previous generations could not have imagined, and the ultimate success, if there is one, might not be a destination we reach, but a transformation we undergo, becoming something that today we can only gesture toward with inadequate words. There is a danger in this kind of thinking, and we should acknowledge it honestly. The contemplation of cosmic destiny can become an escape from present responsibility. If the ultimate goal is so magnificent, so far beyond anything we can achieve in our lifetimes, then perhaps our little struggles here and now do not matter so much. Perhaps we can be forgiven for not trying too hard, for not sacrificing too much, for letting someone else worry about the future. This is a temptation we must resist. The future does not take care of itself. It emerges from the accumulated choices of countless individuals, each deciding how much effort to invest, how much risk to accept, how much to sacrifice for those who will come after. The magnificent possibilities we have been contemplating are exactly that, possibilities. They will not become actualities unless someone makes them happen, and that someone includes us, right here, right now. The Type 7 civilizations of the far future, if they ever exist, will look back on our era as a crucial moment, a bottleneck through which the entire cosmic enterprise had to pass. They will know whether we succeeded or failed. They will know what choices we made and what consequences followed. They will know us more intimately than we know ourselves because they will see us within the context of everything that came after. What will they see? Will they see a species that rose to its challenges, that put aside its differences, that reached for the stars with courage and wisdom? Or will they see a species that squandered its potential, that fought over trivialities while existential risks accumulated, that extinguished itself in a paroxysm of short-sighted foolishness? We do not know. The story is still being written. The outcome is still uncertain. And that uncertainty is not a cause for despair. It is the space in which our agency operates. It is the gap between the possible and the actual that our choices can help to close. As we prepare to examine the Fermi paradox directly, to confront the silence of the cosmos and ask what it means for our own future, let us carry with us this sense of cosmic significance. We are not just curious apes trying to understand our world. We are potential ancestors of something vast and wonderful. We are the seed from which a tree might grow that fills the universe with light. Whether that tree grows or withers depends on what we do now. The weight of that responsibility is heavy, but it is also the source of our deepest meaning. The silence and its meanings. We have travelled across the Kardashev Scale from the modest ambitions of planetary mastery to the godlike possibilities of reality engineering. We have seen what intelligence might become if it survives and grows across cosmic timescales. We have glimpsed destinations so wonderful that they approach the limits of what language can express. And now we must confront the question that has shadowed this entire journey. If such magnificent possibilities exist, if the path from microbe to cosmic mind is open, then why does the universe appear so empty? Why, when we scan the heavens with our most sensitive instruments, do we hear nothing but silence? This is the Fermi paradox, named after the physicist Enrico Fermi, who, during a casual lunch conversation in 1950, suddenly asked his colleagues a question that has haunted astronomy ever since. Where is everybody? The question seems simple, but its implications are profound. If intelligent life is not extraordinarily rare, if civilizations can survive and expand, if even a small fraction reach Type 2 or Type 3 status, then the galaxy should be teeming with observable activity, and yet we see nothing. The contradiction demands explanation. The numbers that frame the paradox are striking. The Milky Way galaxy is approximately 13 billion years old. It contains hundreds of billions of stars, many of which are older than our Sun, and have had billions of years more than Earth to develop intelligent life. Even if the probability of intelligence arising on any given world is tiny, the sheer number of opportunities should have produced millions of civilizations by now. Even if most civilizations destroy themselves, the ones that survive would have had ample time to colonize the entire galaxy many times over. Consider the mathematics of galactic colonization. If a civilization expands at even 1% of the speed of light, which is slow by the standards we have been discussing, it could cross the galaxy in about 10 million years. That sounds long, but it is an eye blink compared to the galaxy's age. A civilization that arose just a few percent earlier than humanity in cosmic history would have had time to colonize every star in the galaxy and build Dyson swarms around all of them. The energy signatures of such activity should be unmistakable. Yet we see natural stars, natural galaxies, natural cosmic processes. Where is the evidence of intelligence? The possible answers to this question fall into several categories, and each has implications for our own future. The first category suggests that intelligence is far rarer than we have assumed. Perhaps the emergence of life from non-living matter is extraordinarily improbable, a fluke that has occurred only once or a handful of times in the entire history of the universe. Perhaps the evolution of complex cells, or of multicellular organisms, or of intelligence, faces barriers so severe that almost no lineage ever crosses them. If any of these transitions is sufficiently improbable, then we might be alone simply because the dice have only come up favourable in our case. This is the optimistic interpretation from a survival perspective, though it is lonely. If the great filter is behind us, then we have already passed the hardest test. The future is open. We can expand without fear that countless others have tried and failed. The silence is not a warning, but a testimony to our exceptional good fortune. But there is another possibility, one that is far more troubling. Perhaps intelligence is not rare at all. Perhaps civilizations arise frequently, develop technology, reach for the stars, and then something stops them. Something prevents them from filling the galaxy with their presence. Something kills them, or transforms them, or contains them before they can spread, beyond their home systems. This is the interpretation where the great filter lies ahead of us. We have not yet faced the test that others have failed. We are marching toward a danger that we do not yet see, a trap that has claimed countless civilizations before us. The silence is not evidence of our uniqueness. It is evidence of the near universality of civilizational failure. How would we distinguish between these possibilities? The answer, frustratingly, is that we cannot do so with current information. We have only one example of life arising, one example of intelligence developing, one example of technological civilization existing. With a sample size of 1, we cannot calculate probabilities. We cannot determine which transitions are easy and which are hard. We are flying blind, unable to know whether we are the first or the latest in a long line of failures. But we can reason about the structure of the problem, and that reasoning suggests some uncomfortable conclusions. If the great filter is behind us, it should have been spectacularly difficult to pass. Otherwise, other civilizations would have passed it as well, and we would see evidence of their existence. The filter must be something so improbable that in a galaxy of hundreds of billions of stars over billions of years, it occurred only once or a handful of times. This is a very high bar. Every discovery that makes the emergence of life seem more likely, every planet found in a habitable zone, every organic molecule detected in space, makes this explanation less plausible. The more we learn about the universe, the harder it becomes to believe that we are alone by cosmic accident. If the great filter is ahead of us, it must be something that reliably destroys or contains civilizations that reach our approximate level of development. It must be something we have not yet encountered but are approaching. And it must be something that no civilization has ever overcome, or at least that civilizations overcome so rarely that the galaxy remains apparently empty despite billions of years of opportunity. What could such a filter be? We discussed candidates in an earlier chapter: nuclear war, climate collapse, pandemic disease, artificial intelligence. Each of these is a plausible threat, but none seems quite sufficient to explain the totality of the silence. Surely some civilizations would avoid nuclear war. Surely some would solve their climate problems. Surely some would develop AI safely. For the silence to be total, the filter must be essentially universal, something that catches everyone, or nearly everyone, regardless of their particular circumstances. This line of reasoning has led some theorists to propose that the filter might not be a single barrier but a series of obstacles, each of which claim some fraction of civilizations that attempt to pass. Perhaps half of technological civilizations destroy themselves with nuclear weapons. Of those that survive, perhaps half are destroyed by climate collapse. Of those that survive, perhaps half are destroyed by AI. The cumulative effect of multiple filters, each individually survivable but collectively devastating, might explain why the galaxy appears empty, even though no single filter is 100% effective. But there is a third category of explanation, one that does not rely on civilizations failing or being destroyed. Perhaps advanced civilizations exist in abundance, but are invisible to us for reasons we do not yet understand. This is the dark forest hypothesis we touched on earlier, and it deserves fuller examination. The idea is that the galaxy might be a dangerous place, filled with civilizations that have learned the hard way that revealing yourself is suicidal. In such an environment, the optimal strategy is silence. Hide your signals, mask your energy signatures, do nothing that might draw the attention of potential predators. The logic is disturbingly plausible. In a galaxy where civilizations can destroy each other across interstellar distances, trust is impossible to establish. You cannot know whether an alien civilization is friendly or hostile. You cannot know whether your signal will be received by benevolent neighbors or genocidal empires. The safe choice, the only reliably safe choice, is to remain hidden. Civilizations that broadcast their existence are eliminated. Civilizations that remain silent survive. Over millions of years, natural selection ensures that only the silent remain. If this hypothesis is correct, the silence is not evidence of absence. It is evidence of prudence. The galaxy might be teeming with Type 2 and Type 3 civilizations, all maintaining perfect silence, all watching and listening but never speaking. We might be surrounded by intelligence that we cannot detect, because it has learned, through bitter experience, that detection means destruction. This possibility has disturbing implications for our own behavior. Humanity has been broadcasting radio signals into space for about a century. We have sent deliberate messages toward nearby stars. We have put plaques on spacecraft that describe Earth's location and human biology. If the dark forest hypothesis is correct, these actions may have been extremely unwise. We may have been shouting our presence into a jungle full of predators, but there are reasons to doubt the dark forest scenario. The logic assumes that civilizations can reliably destroy each other across interstellar distances, and that the risk of such destruction is high enough to justify eternal silence. Neither assumption is obviously true. The energy required to sterilize a planet across light years of space is enormous. The timescales involved in interstellar conflict are measured in decades or centuries. A civilization capable of Type 2 energy harvesting might be effectively invulnerable to attack, or might be able to spread so widely that no attack could eliminate all of its instances. The dark forest assumes a particular set of capabilities and vulnerabilities that might not apply to advanced civilizations. Another possibility is that advanced civilizations transcend the desire for expansion altogether. Perhaps once a civilization solves the problems of survival and scarcity, once it achieves the energy abundance of Type 2 or beyond, it loses interest in spreading further. Why colonize new star systems when you already have everything you need? Why explore the galaxy when virtual realities offer infinite novelty without the inconvenience of interstellar travel? Perhaps advanced civilizations turn inward, becoming increasingly absorbed in their own pursuits, until they become effectively invisible to younger civilizations still struggling upward. This is the lotus eater hypothesis, and it has a certain intuitive appeal. We can already see hints of it in our own society. As entertainment becomes more immersive and engaging, the drive to explore physical reality diminishes for many people. Virtual worlds offer experiences that physical reality cannot match. Advanced civilizations might have virtual realities so compelling that the physical universe becomes an afterthought, a substrate to be maintained rather than a frontier to be explored. But this explanation also has problems. It requires that all civilizations make the same choice, that none among the billions that might exist choose to expand despite having the capability. It seems implausible that the preference for inward exploration would be so universal. Even if 99% of civilizations turn inward, the remaining 1% should still be visible. 1% of billions is still millions. Where are they? Perhaps the answer is simpler and more humbling. Perhaps we are looking but not seeing. Perhaps the signatures of advanced civilizations are present in our data but unrecognized because we do not know what to look for. We assume that advanced technology will produce certain kinds of signals, certain kinds of energy signatures, certain kinds of megastructures. But an intelligence millions of years ahead of us might use technologies that do not produce the signatures we expect. They might communicate through channels we have not conceived. They might build structures that are invisible to our instruments. Consider the history of our own technology. A century ago, radio was cutting edge. 50 years ago, it was television. Today, we have the internet and wireless networks and streams of data that a 19th century scientist could not have imagined, let alone detected. An alien scientist a century ago, scanning Earth for signs of technology, might have detected our radio broadcasts. An alien scientist today, using the same methods, might find Earth strangely quiet as we shift to more efficient, less leaky forms of communication. Advanced civilizations might have completed this transition long ago. Their communications might be encoded in ways that appear as noise to us. Their energy usage might be so efficient that it produces no detectable waste heat. Their megastructures might be designed for stealth rather than visibility. We are looking for campfires and they are using something that leaves no trace. This is not a comforting explanation. It means we cannot know whether we are alone or surrounded. It means the silence carries no information, tells us nothing about our own prospects. We are blind and deaf to whatever might be out there, and our blindness tells us nothing about whether anything is there at all. Perhaps the most honest answer is simply that we do not know. The Fermi paradox has resisted resolution for 75 years because none of the proposed explanations are fully satisfying. Each has problems, each makes assumptions that might be wrong. The silence remains a genuine mystery, an open question that admits of no confident answer. What we can say is that our choices matter regardless of which explanation is correct. If the filter is behind us, we should press forward with confidence, knowing that the future is ours to claim. If the filter is ahead of us, we should redouble our efforts to identify and mitigate existential risks, to ensure that we are not the next entry in the ledger of civilizational failure. If the dark forest is real, we should be cautious about what we broadcast while developing the capabilities that might let us survive contact. Whatever the truth, our best response is the same: develop wisely, expand carefully, prepare for challenges we cannot yet foresee. The silence of the cosmos is not an answer, it is a question directed at us, asking what we will do with the gift of existence. The universe has given us a chance to grow from planetary infancy toward cosmic adulthood. What we make of that chance depends on the choices we make now, in these crucial centuries when our trajectory is still being determined. The stars are waiting to see what we will become. The road before us. We have travelled far in our exploration, from the fundamental concept of measuring civilizations by their energy use to the dizzying heights of reality engineering and cosmic consciousness. We have confronted the great filter and its implications, examined the silence of the cosmos and its possible meanings, and glimpsed what intelligence might become if it survives to fulfill its potential. Now we must return to the present, to this moment in history when all of these possibilities remain open, and our choices will determine which of them become real. The year is 2025, and humanity stands at a crossroads unlike any it has faced before. We possess technologies powerful enough to transform our world or destroy it. We understand the nature of our challenges more clearly than any previous generation. We have the resources, if we choose to deploy them, to begin the long climb toward Type 1 civilization and beyond. The question is whether we will make that choice, whether we will summon the collective will to do what needs to be done. Let me be specific about what that would entail. The transition to Type 1 requires a complete transformation of our energy infrastructure. We currently derive about 80% of our energy from fossil fuels, a dependency that is destroying our climate and that cannot be sustained regardless of its environmental costs. The fossil fuel era must end, not because of moral preferences, but because of physical necessity. Either we end it on our terms through deliberate transition to clean energy, or nature ends it on its terms through resource depletion and climate catastrophe. The good news, and there is good news, is that the technologies we need for this transition are advancing rapidly. Solar power has become the cheapest source of electricity in history, its cost falling by orders of magnitude over the past few decades. Wind power is similarly cheap and continues to improve. Battery technology is advancing year over year, enabling the storage that makes renewable energy reliable. Electric vehicles are displacing internal combustion engines across the transportation sector. The pieces of a clean energy future are falling into place, but the most transformative technology of all remains on the horizon. Fusion power, the energy source that lights the stars, is closer to practical realization than at any time in human history. We touched on this earlier, but it deserves fuller attention now because fusion is not just another energy source. It is the key that unlocks everything else. The ITER project in southern France represents humanity's most ambitious attempt to prove that fusion power is achievable at scale. 35 nations have collaborated on this endeavour, contributing technology and expertise and funding to build a device that will demonstrate net energy gain from fusion reactions. In August of 2025, the assembly of ITER's core entered its critical phase, with a vacuum vessel taking shape that will contain plasma hotter than the centre of the Sun. ITER is designed to produce 500 megawatts of fusion power from just 50 megawatts of input heating power, a tenfold energy gain that would prove the basic concept beyond any doubt. It will not generate electricity for the grid. That is not its purpose. Its purpose is to learn, to test, to refine the technologies that will enable future reactors to power civilization. Behind ITER stands DEMO, the demonstration power plant that will translate ITER's lessons into practical electricity generation. Behind DEMO stands a future of fusion power plants distributed across the globe, providing clean, abundant energy to every nation willing to build them. The fuel for these plants, deuterium extracted from seawater and tritium bred from lithium, is effectively inexhaustible. The oceans contain enough deuterium to power human civilization at levels far beyond current consumption for billions of years. But ITER is not the only fusion program making progress. The National Ignition Facility in the United States achieved ignition in 2022, using laser-based inertial confinement rather than magnetic confinement. Since then, they have recorded energy gains exceeding 120% in repeated experiments. China's experimental advanced superconducting tokamak has sustained plasma at 158 million degrees Celsius for over 15 minutes, pushing the boundaries of what magnetic confinement can achieve. Private companies are also entering the race. Helion Energy claims to have produced electricity directly from fusion reactions in their 7th-generation prototype. Commonwealth Fusion Systems is building Spark, a compact high-field tokamak designed to achieve net energy gain on a faster timeline than ITER. T Technologies is developing an alternative approach based on field-reversed configurations. The fusion landscape is more dynamic and competitive than at any point in history. If fusion succeeds, and the technical progress suggests that it will, the implications cascade through every aspect of our civilization. Energy ceases to be a constraint. Desalination becomes economically viable at any scale. Synthetic fuel production from atmospheric carbon becomes practical. Industrial processes that currently rely on fossil fuels can be electrified or converted to hydrogen. The climate problem becomes solvable not through sacrifice but through substitution, replacing dirty energy with clean energy that is also cheaper and more abundant. But energy transformation alone is not sufficient to pass the great filter. As we discussed earlier, the other crucial element is becoming a multiplanetary species. A civilization that exists on only one world remains vulnerable to extinction from countless possible catastrophes. Asteroid impact, supervolcanic eruption, engineered pandemic, nuclear war, unfriendly artificial intelligence. These threats and others we have not anticipated could end human civilization if we remain confined to Earth. This is why the SpaceX Mars program matters so much. It is not just about adventure or exploration, though those motivations are valid. It is about civilizational insurance, about ensuring that whatever happens to Earth, humanity survives. The May 2025 presentation at Starbase laid out a roadmap with unprecedented specificity. Uncrewed Starship landings on Mars in 2026, human missions as early as 2028, a self-sustaining colony by 2050. These timelines may slip. Space is hard, as the saying goes, and unexpected challenges always emerge. But the overall trajectory is clear. SpaceX is building the vehicles and developing the capabilities that could make humanity a two-planet species within the lifetimes of people alive today. The first settlers on Mars may be born in the next few years, maybe children right now, maybe listening, to this very exploration of what their mission means. The plan calls for approximately 1 million tons of infrastructure to be transported to Mars, enabling the construction of everything needed for self-sufficiency. Power generation from solar panels and eventually nuclear reactors, resource extraction from Martian soil and atmosphere, manufacturing capability to produce tools and habitats from local materials, agriculture in pressurized greenhouses, growing food from Martian regolith enriched with terrestrial nutrients, a complete industrial ecosystem, able to survive and grow even if all contact with Earth were lost. This is not science fiction. The technologies required are extensions of capabilities we already possess. Starship is real, has flown multiple test missions, and is approaching operational readiness. The physics of interplanetary travel is well understood. The challenges are engineering challenges, immense but tractable, given sufficient resources and determination. The question is not whether Mars colonization is possible. The question is whether we will commit the resources to make it happen. Elon Musk has estimated that achieving self-sustaining status on Mars would require about 7 to 9 years after landing the first human cruise. This estimate may be optimistic, but even if it takes twice as long, we could have a resilient human presence on Mars before the middle of this century. That is within the planning horizon of governments and corporations. That is not some distant future, but a near-term goal that current decisions can affect. The Mars program also represents a forcing function for other technologies that will be valuable regardless of interplanetary expansion. Closed-loop life support systems, advanced robotics, in-situ resource utilization, radiation protection, long-duration human spaceflight. These capabilities have applications on Earth and in near-Earth space as well as on Mars. The effort to colonize Mars will accelerate development across a broad technological front. But even fusion and Mars colonization, transformative as they would be, do not address all the filters we face. Artificial intelligence remains the wild card, the risk that could either accelerate our progress toward Type 1 or terminate our civilization before we get there. The development of AI safety practices and governance frameworks is arguably as important as any technical advancement. We discussed Michael Garrett's paper earlier, with its troubling estimate that technological civilizations might survive only 200 years on average after developing advanced AI. If this estimate is even approximately correct, we are running out of time. We must develop AI that remains aligned with human values and subject to human control, and we must do so before more capable and potentially dangerous systems emerge. This is an area where progress is harder to measure than in energy or spaceflight. There are no obvious milestones like ignition or orbital insertion. The work is conceptual and theoretical, involving difficult problems in computer science and philosophy that may not have clean solutions. But the stakes are high enough that we must try. Every insight into AI alignment, every improvement in governance, every step toward international coordination on AI development reduces the probability that AI becomes the filter that ends our story. The good news is that the AI safety community has grown substantially in recent years. Research institutions, government agencies, and leading AI companies are investing resources in understanding and mitigating AI risks. The conversation has moved from fringe concern to mainstream priority. This does not guarantee success, but it increases the probability that we will navigate the AI transition safely. If we succeed in these efforts, if we master fusion and colonize Mars and develop AI safely, what comes next? The answer is continued growth up the Kardashev scale, at a pace that will seem dizzying to those who think in terms of years rather than centuries. Type 1 civilization, with full mastery of planetary energy resources, might be achieved within 1 to 3 centuries. From there, the expansion into the solar system would follow naturally. Asteroid mining, space manufacturing, habitats in orbit around Earth, and at the Lagrange points, these developments would support a population measured in billions living off Earth, accessing resources far greater than Earth alone can provide. Type 2, civilization, harnessing the full energy output of the Sun, might require a few thousand years to achieve. Dyson swarms would gradually accumulate around the Sun, capturing solar energy at scales that dwarf current human consumption by factors of billions. The entire solar system would become the domain of human activity, with worlds terraformed and habitats constructed to support populations measured in trillions. Type 3 and beyond lies so far in the future that any predictions are pure speculation. But the point is that there is a path. The physics does not forbid our advancement. The engineering challenges, though immense, are finite. If we survive the next few centuries, if we pass through the bottleneck that threatens all technological civilizations, then the future opens before us without obvious limit. This is the message of the Kardashev Scale, and it is a message of profound hope, despite all the dangers we have discussed. We are not trapped. We are not doomed. The universe is not hostile to intelligence, but is, in a sense, waiting for intelligence to arise and claim it. The silence of the cosmos might mean that this claiming is rare, but it does not mean it is impossible. Someone has to be first. Someone has to pioneer the path that others might follow. Perhaps that someone is us. The choices we make in the coming decades will determine whether we fulfill this potential or become another entry in the ledger of civilizational failure. Every investment in clean energy, every launch toward Mars, every advance in AI safety moves us toward the future we want. Every delay, every distraction, every failure of political will moves us toward the future we fear. We are not spectators in this drama. We are participants. The outcome depends on what we do, what we advocate for, what we build, what we demand from our institutions and leaders. The Kardashev Scale is not just a measure of what civilizations can achieve. It is a roadmap for what we must achieve if we want to survive and flourish. The stars are not out of reach. They never were. The question was always whether we would reach for them with sufficient determination and wisdom. That question remains open, and the answer depends on us. The weight of stars. When Nikolai Kardashev first proposed his scale in 1964, he was trying to solve a practical problem. How do you search for signals from civilizations you cannot imagine? How do you recognize technology that might be millions of years more advanced than your own? His answer, elegant in its simplicity, was to focus on the one thing all civilizations must have in common: energy. The laws of physics are the same everywhere. Thermodynamics applies to aliens as surely as it applies to us. By measuring energy consumption, we could create a universal yardstick for advancement, one that transcends all the cultural and biological differences that might otherwise make extraterrestrial intelligence unrecognizable. But Kardashev's scale turned out to be more than a search tool. It became a mirror in which humanity could see itself, not as we are, but as we might become. It became a ladder connecting our present limitations to our potential greatness. It became a framework for thinking about what intelligence means on cosmic scales, what existence might mean when the constraints we take for granted have been transcended. We have climbed that ladder together in this exploration, rung by rung, from the modest achievements of planetary civilization to the vertiginous heights where intelligence merges with reality itself. We have seen what a Type 1 civilization would look like, with its mastery over weather and climate, its fusion-powered abundance, its freedom from the scarcity that has defined all previous human existence. We have contemplated Type 2, with its Dyson swarms encircling stars, its populations counted in trillions, its timescales measured in millennia rather than decades. We have stretched our imaginations further still, to Type 3 civilizations spanning galaxies, to Type 4 and 5 commanding the resources of universes and multiverses, to Type 6 and 7, where the distinction between creator and creation dissolves into something that religious traditions might call divine. These higher levels may never be reached. They may not even be meaningful in the way we imagine, but contemplating them changes how we see ourselves. It expands the horizon of the possible. It reminds us that we are participants in something vast and old and strange, something that might lead anywhere or nowhere depending on choices that are partly ours to make. The Great Filter has been our constant companion on this journey. At every level of the Kardashev Scale, we have asked whether this is where civilizations fail. Is it the transition to planetary mastery, when technologies become powerful enough to destroy as easily as to create? Is it the leap to stellar civilization, when the distances and timescales exceed what biological minds can manage? Is it somewhere beyond, in challenges we have not yet conceived? The silence of the cosmos suggests that the filter is real and that it is effective. The question is where it lies and whether we can pass it. I have not hidden my belief that the filter is ahead of us, not behind. The evidence suggests that planets are common, that organic chemistry is ubiquitous, that life probably arises frequently wherever conditions permit. If the filter were in our past, it would need to be almost impossibly difficult to explain why we are apparently alone. It seems more likely that civilizations like ours are common enough to arise many times per galaxy, but that something stops them before they can spread and flourish. We are walking toward that something. We do not know exactly what it is, but we know it has claimed everyone who came before us. This knowledge is both terrifying and empowering. Terrifying because it means our survival is not assured, that forces we do not fully understand threaten to cut short our cosmic journey before it truly begins. Empowering because it means our choices matter, that what we do in the coming decades could determine whether humanity is remembered as a flash of intelligence that briefly lit the darkness, or as the ancestor of something magnificent that endures for billions of years. The threats we face are real, but not inevitable. Nuclear weapons exist, but nuclear war is a choice that humans can decline to make. Climate change is accelerating, but clean energy technologies are advancing even faster. Artificial intelligence is developing rapidly, but so is our understanding of how to make it safe. Becoming multiplanetary is technically feasible, and serious efforts are underway to make it happen. The filter is not a wall we cannot climb, it is a test we might fail, and tests by their nature can be passed if we prepare sufficiently. I think about the researchers at ITER, welding together the vacuum vessel that will contain plasma hotter than the sun. I think about the engineers at SpaceX, building the vehicles that might carry our species to Mars. I think about the scientists studying AI alignment, trying to ensure that the minds we create remain our partners rather than our replacements. I think about everyone who is working, in ways large and small, to push humanity toward a future worth wanting. These are the people who are fighting the great filter. These are the people on whom our survival depends. And I think about you, whoever you are, wherever you are listening from. You are part of this story too. The choices you make, the priorities you advocate for, the future you help to build, all of it matters. We're at a moment in history when individual actions can have consequences that echo across centuries. The investments we make now in clean energy will determine what climate our grandchildren inherit. The space programs we support will determine whether humanity is confined to one world or spread across many. The governance frameworks we develop for AI will determine whether thinking machines are our greatest achievement or our final mistake. This is not a burden I place on you alone. It is a burden we all share collectively as a species becoming aware of its own significance and fragility. We did not ask for this responsibility. It came to us simply by being alive at this particular moment in cosmic history. This inflection point where the trajectory of intelligence might ascend toward the stars or terminate in the silence that already fills the void. But the responsibility is ours nonetheless, and how we discharge it will be judged by whatever comes after. I want to leave you with an image. Picture the Milky Way galaxy as it might look from outside, from some vantage point beyond its spiral arms. You see hundreds of billions of stars arranged in sweeping patterns, rotating slowly around a central bulge. Most of those stars are orbited by planets. Many of those planets could support life. And yet, from this outside perspective, the galaxy appears entirely natural. There are no obvious signs of engineering. No Dyson swarms dim the light of stars. No communications networks pulse with intelligent signals. The galaxy looks pristine, untouched, as if no mind has ever contemplated its vastness from within. This is what we see when we look at other galaxies through our telescopes. They all look natural. They all look empty. Billions of years of cosmic history, trillions of potential worlds, and apparently no one has filled the darkness with light. Now picture what the galaxy could look like if intelligence succeeds. Stars wrapped in energy-harvesting structures, their light captured and put to use. Planets terraformed into gardens, habitats scattered through every stellar system. Communication networks linking worlds across tens of thousands of light-years. A galaxy that has been touched by mind, shaped by purpose, made into something more than dead matter cycling through meaningless patterns. Which galaxy do we want to help create? The empty one or the filled one? The natural one or the engineered one? The silent one or the one that rings with the voice of intelligence? I know which one I want. I suspect you do too. Or you would not have travelled this far with me, through the mathematics of energy scales and the mysteries of the great filter and the sublime possibilities of cosmic evolution. We want the galaxy to be alive. We want intelligence to flourish. We want meaning to exist not just in the brief flickering of individual minds, but woven into the fabric of reality itself. And that wanting is not passive. It is a commitment. It is a decision to work toward the future we desire, rather than accepting whatever future arrives by default. It is a recognition that we are the ones who will determine whether the galaxy remains silent or fills with light. The Kardashev Scale is not just a measure of what has been achieved. It is a measure of what remains to be done. Every step up the ladder represents challenges overcome, dangers navigated, filters passed. We stand at the bottom of that ladder now, a Type 0.73 civilization just beginning to understand what it might become. The rungs above us lead toward futures we can barely imagine, toward possibilities that would transform not just our species but the meaning of existence itself. The climb will not be easy. There will be setbacks and failures. There will be moments when it seems impossible, when the challenges are too great and the risks too severe. But the alternative is not comfort. The alternative is extinction, or eternal stagnation, or some other fate that leaves the universe empty of the intelligence that might have filled it. I choose the climb. I hope you do too. Thank you for joining me on this journey through the Kardashev Scale, from the first tentative steps toward planetary mastery to the ultimate visions of cosmic consciousness. Thank you for your curiosity, your patience, your willingness to grapple with ideas that stretch the mind and challenge the imagination. Thank you for being part of the community of minds that is trying to understand our place in the universe and how we might fulfill our potential within it. If this exploration has sparked something in you, a new way of seeing, a renewed commitment to the future, please share it with others. The ideas we have discussed are not just intellectually interesting, they are practically urgent. The more people who understand what is at stake, the better our chances of making the choices that lead toward survival and flourishing. And as always, if you found value in what we have explored together, please take a moment to like and subscribe. It helps this message reach others who might need to hear it. It helps build the community that will carry these ideas forward into the future we are trying to create. The universe is waiting, the stars are calling, and somewhere out there, in the vast darkness between galaxies, the light we kindle might be the first light of many, the beginning of something that spreads and grows and lasts until time itself grows old. May we find the wisdom to make it so. Good night, and may you dream of stars. Disclaimer: this content is intended for educational and entertainment purposes. The scientific concepts discussed represent current understanding and are subject to revision as new discoveries are made. The speculative elements regarding advanced civilizations and future technologies are thought experiments rather than predictions. Always consult primary scientific sources for the most current and accurate information on the topics covered.